are able to stay on time today. Thank you all for being here with us today. Glad to have all of you here participating. This is the second session in this year's Weather and Society Conference. There are 5 sessions altogether, so we have another tomorrow and a couple on Thursday. So hopefully you'll able to make it out to some of the additional sessions. Today we're focusing on transdisciplinary science to enhance weather services. So I hope you're in the right place. Isha, could you put the rules up here? So what we're going to do, I'm going to go ahead and kind of give an overview of how we would like the afternoon to run. And then I will introduce our keynote speaker. So these are just some rules we have to help make sure everything flows smoothly and that everybody can hear the speaker, listen and pay attention and have an opportunity to actually ask questions and get involved a bit. So we're going to ask everybody to keep muted throughout the session. So if you do have questions and things, we're going to ask you to put questions in the chat. You can have your camera on if you wish, but it's certainly not required. We ask that you be respectful and polite to everyone. And do note that this session is going to be recorded. One of the things we're going to try and do, and this is out of respect to everybody that is participating, you will probably note that we will have participants from all over the globe, and we have people that means we have people at different time zones. Some people are up very early, some people are up very late. So we want to make sure that we really stick to the time. And so we ask that you follow the moderators in doing that, and that is just respectful to the other people in the group and help ensure that everybody has an opportunity to participate. If you have any questions at any time, please go ahead and put them in the chat. That will be moderated, and at the end of the speakers, we'll have an opportunity to answer questions, share those with the speaker of the keynote or any of the other speakers. All right. So people are still rolling in, so that's great. That's very exciting. I'm going to go ahead and introduce our keynote speaker who is here with us today, Dr. Victoria Reyes Garcia, who is at the Catalan Institute for Research and Advanced Studies and sits in the Autonomous University of Barcelona. She received a PhD in anthropology from the University of Florida, and her research focuses on indigenous and local knowledge systems, particularly in relation to the natural environment and on the relevance of these knowledge systems to understand and deal with the climate and environmental crises. She co-created the Laboratory of Analysis of Social Ecological Systems in a Global World, and this research group analyzes the impacts of global change on socio-ecosystems. Her latest ERC-funded project, which I believe is what she's talking about today, studied local perceptions of climate change impacts.
So apologies for that, everybody, and good morning, afternoon, or evening, depending on where you are. So as Don introduced in his introduction, he said, I'm going to be talking about climate change impacts and how indigenous people and local communities around the world perceive them. And the main message that I want to convey is that local studies like the anthropologists do can bring a global perspective to climate change impacts. And I also want to say before I start that this is a work that I have done as a part of an ERC, European Research Council funded project. It was called LICHI. And of course, no one does anything alone. None of them is done alone. And here are the names of the people who conducted some of the case studies that I'm going to be talking about and who are part of what we call the LICHI consortium. So the LICHI project, okay, now it's not moving. Yes. The LICHI project is about indicators of climate change paths and how this can contribute to local knowledge and policy risk and policy. So the basic idea, or where we started with the LICHI project, is that there is a global net of weather station that is distributed around the world, but this network, these weather stations are unequally distributed. And there are many regions in the world where there are very little coverage. So if you see the map, I'm just double checking now, you see the map, right? I'm moving the slides. Yes, okay. So if you see the map, the areas that are darker is areas where you have more weather stations of the ones that are using to make the climate projections. But there are many places in the world that you have like lighter colors, and these are places where you have less coverage. So the intuition of the Lychee project is that in these areas, there are no weather stations, but there are people with local knowledge and that have lived there for many, many years and for generations that have understanding on how the things have changed and how weather is changing, and they have ground information of changes that are occurring, right? So because in those areas there are no weather stations, also the modelings that use information from these meteorological stations are less precise, right? Because they have to do more interpolations and data is less precise for these areas. So we wanted to see whether we were able to put all this, to use this information of local knowledge at a global scale. Now, we were not the first ones on having this idea. There is already an existing, or there was one before we started the project, an existing literature on case studies reporting local perceptions on climate change impacts and how these people, how changes in the weather were affecting to people. But and I'm putting here some of the early examples of research looking at local perceptions of climate change impacts. But one of the problems with this literature was that they were unequally distributed. So it was kind of like convenient wherever the researchers had the ability to conduct their work. And also in every location, people use different methods, right? There was not a coordinated effort. It's not like, I mean, if people taking information from weather stations, one was putting the thermometer on the sun and the other in the shadow and the rain. So, I mean, there was not like a precise method that everyone was using, and therefore the data that was being collected was not really comparable, right? So that was the background that put us to prepare this Lychee project. And there were three main ideas or three main objectives of this project, right? One was to see whether local knowledge could really contribute to understand climate change and its impacts. Can we really see patterns or that are observable across different societies, or it's just like everyone is reporting different things? And then how can we bring this information or these insights to international climate change policy? And this was kind of like also an important goal, because up to that moment, many of the case studies are treated as just like punctual data, right? I mean, it's like, okay, this is happening for these indigenous people or for this local community, but how does this is going to inform like the global policy? So we wanted to bring this idea that no, these local insights could inform global policies. And then we also wanted to create this network of people, researchers, and also more people that are more applied work practitioners, NGOs that are interested in indigenous knowledge and climate change. So these were our objectives. To achieve that, the main methodological strategy was the collection of what we call locally meaningful but cross-culturally comparable data. So we wanted to collect data that makes sense at the local level. So in some areas there are droughts, or in some areas there's water fountains are drying, or the winds from the north are coming. But that at the same time we could compare across case studies. Can we say that indigenous people are seeing the same effects of impact, the same impacts in their lands or not? And to do that, we devised an strategy that was based And first, in local partnerships, we work with people that were working in areas. This is kind of like methods that come a lot from anthropology, right? So we were kind of like working with local people, with our local partners. We did a lot of participant observation. We did focus group discussions, structures, interviews, right? But the main idea here was to collect data in 50 sites. So in this map, you see the distribution of the sites that were distributed across climate zones and livelihoods. So originally, in our original design, we wanted to have sites that cover the 5 main climate zones, no, arid areas, temperate areas, tropical, polar, snow, and that cover the 4 main livelihood strategies of people who are in direct contact with the environment. So we were basically working with, we wanted to work with societies that rely on nature mainly for their livelihood, because that was a condition to actually understand what is happening in the environment around them. Obviously, the distribution of societies was not perfectly like distributed across size, because some of the livelihood activities like fishing you don't have in desert areas, right? So you could not have like a perfect distribution between societies, between livelihood activities and climate zones. But in this map, you see like the wide distribution across area. Another issue there was that this project started with the COVID pandemic. So some of the sites, for example, in the US, we had like 3 sites, but they have to be canceled because of COVID restrictions, and then couldn't start. But that was the concept, right? Look at sites of people who live in direct dependence of the natural environment and are across climate zones and livelihoods. And then the other kind of like important concept that helped us in this project was this idea of creating this lychee tree, which is what you have in the other side of the slides. And this is not for you to see, but it's just to conceptualize this idea that when we were interviewing people in these interviews that we were conducting, we were asking people, can you tell me, that was our main question, can you tell me changes in the local environment that you have seen since you were a kid? So people were reporting changes in the environment from a time period, their lifetime period, and then we asked what has driven that change, and only eventually, if the driver of the change was related to climate, to temperature or climate change, we consider that as a change that was climate driven, no? As a climate change. So basically, people report observations, and we classify these observations in these 3 that basically classify observations, saying, okay, is the observation in the atmospheric system, is observation in the physical system, is observation in the life system, and then in the atmospheric system, for example, we have temperature, and is the observation reporting to medium temperature at night, so we kind of have like this classificatory tree that basically classify any observation of change in the environment in this tree, and this is what allowed us to compare across site, right? Because the observations were very detailed to the site, but then this tree allowed us to classify the observations. So this was kind of like very roughly the method that we use, and I just want to focus now on the main results, on the main questions that we were asking with this project. The first one relates to how do indigenous people and local communities experience, understand, and describe climate change impacts. The second one has to do more with adaptations and how people adjust or cope with these impacts. And the last one, which was not really planned before we started the project, are some reflections on this process of weaving the climate knowledge, right, with more local knowledge, right? So the first question, no? How do indigenous people and local communities experience, understand, and describe climate change impacts? So our main result here is that across the 50 sites in where we work, in all the sites, indigenous people, or like all the people that we were working with, reported numerous ongoing, tangible, and situated impacts that providing like a whole holistic view of change. In none of the sites, people say, no, everything is as used to be. This is like when I was a kid, no? People in all the sites experience changes, and changes, some of them here in this graph, some of them are, for example, the Inuit fishermen in the Arctic Canada, they report less snowfall and more frequent thin sea ice. Or, for example, the herders in the Carpathian regions in Romania, they say that there were less but more intense rainfall patterns, right? Or, for example, Aka people in China, in Yunnan, they said that they have noticed changes in the taste of the tea leaves that they grow because there is less rain, right? So there were a myriad of changes, but in all the sites, there were some of these changes, and they were situated, right? And here is where the lychee tree that I introduced was very useful, because we were able to classify those situated observations and be able to say something more global, right? For example, we were able to say how many of the changes that people perceive have to do with elements of the atmospheric system. How many of these changes have to do with elements of the physical system, for example, soils, right? Or fresh water. How many have to do with the life system, right? So when we aggregate all those observations that we arrived to more than 1,500 observations, we see that most of them have to do with the atmospheric system, and more with precipitation than with temperature. So precipitation is something that is more noticeable to people. And then after that, observations in the life system are more frequent than observations in the physical system, no? And this has to do with plant cultivation or with terrestrial flora, and this has to do with the livelihood of people, right? Because people will say, oh, for example, now we cannot put the crops at the same time because the rains are not coming, right? Now we have to change our cropping. Or now the animals cannot grow grass in that area because the grass has changed, right? So these were the type of observations. I didn't say that when I am referring to observations in all these cases, these 1,500 observations, these are not observations by individuals. We conducted individual interviews, and then we conducted focus group to verify those informations, right? So every one of these 1,500 site-agreed observations that said in the slide means that someone or several people have told us, and then we conducted focus group, because sometimes in the interviews, some of the information was contradictory, right? Someone say, oh, the wind is coming from the north, and someone say it's coming from the south. And then in the focus group, we were able to say, oh no, in the morning, or whatever it was, no? So this is important, that these are not individual observations, but observations that people in the 50 sites agree. Another of the important findings in answering this question of how people experience and understand these impacts from climate change is that there were a lot of changes that were observed in the life system, in the biological systems, and people were able to report changes in taxon abundance, in phenotype, in phenology, and in the distribution, right? And for many species of animals, no, for plants, for fishes, for mammals, and importantly, we compare these taxa, no? We look at, people say, oh, this plant is not growing, or these birds are not coming anymore, and then we went to the IUCN kind of like lists that they have on species, and we check whether the IUCN consider that they are threatened by climate change, or what's their status. And we observed that many of the species that people report as affected by climate change, they are not in the IUCN list, or they are not reported as climate change driven. And this is important, right? Because we have like two knowledge systems, and they are operating at different scales. IUCN, or like the scientists, let's say, it's not like an organization, it's science in general, are not paying attention to the same organisms that people are paying attention, right? People are telling you some birds, some plants, or mammals that are being affected, and these are not the ones that are concerning scientists, which actually are the ones who are driving the policies later, right? So it's important to see the mismatch, because people might be interested in different species. And one other interesting finding that we have, which was also kind of like a little bit on the side on this project, is that climate change impacts are associated with lower subjective well-being. And this is something very interesting that we were not expecting. As a side on this project, we collected data on subjective well-being. We asked people, from 0 to 10, how happy are you? And we wanted to see how people in small scale societies, how happy they are. And this is something that we publish in PNAS, and that is in the graph on your left, or on my left, where you see like the dots in blue are is the association between income and happiness, right? And you see that the higher the income, the higher the happiness in general. These are the blue dots are countries, right? And the higher the income, the higher, with a logarithm kind of like curve. And the yellow dots are people in our sample, or small scale societies. People in our small scale societies were happier in general than people in all the nations. Okay, so far so good. What does this have to do with climate change and weather? Then we analyze how if there was an association between perception of the severity of climate change and life satisfaction. And this is the other graph that you have on my right, where we find that although people have a very high subjective well-being, although people in the societies we study reported that they were on average quite happy, more than many societies, though when the higher they experience the severity of climate change impacts, the lower their subjective well-being. So there were not many things that affected their subjective well-being, but climate change did. And we thought that was kind of like very telling, no? Like the severity of climate change impact affect their well-being. So another of the findings I will mention briefly is this idea. That was another important finding, that people in our interviews in all the sites recognize climate change impact only as one of the drivers of environmental change. If you remember, when I started the presentation, I said our question was, which changes have you seen in the environment and what drives them, right? So people, sometimes they say, oh yeah, now there is less water because, the rains are coming later, right? The crops cannot grow because the rains are coming later. But sometimes they say, now we cannot grow crops because they have make a dam upriver and there is less water coming and we cannot actually grow our crops, right? So when we put together all the different impacts that they perceive and the drivers and the relationship between all these impacts and drivers, we find, this is only one example on the Chimane, we find that people have a holistic understanding of the issue. It's not that they say, oh, it's hotter now than it was in the past and that's what's driving everything. But there is like all this mixed, and here in this graph, we put, for example, in red, the drivers that are kind of like more social or not related to climate change, governance and technological changes and infrastructure. And in gray, there is like the climate related. In blue is the changes in the physical system, and in green in the life system, right? But you see that every change might be related to all of them, providing, as I say, this kind of like holistic picture. And I want to finish, I think, this first part of the first question, no? How indigenous people and local communities experience and describe climate change impact. That was our first question, in saying that that I'm saying this with very kind of like, or with somehow technical words, right? But people had the voices of the people were very different. No? For example, people will say, "Oh, the plants cook on the ground. The ground is now hot, then it rains, and then it's hot again, and then the seed cooks on the soil," right? So people were not expressing themselves. So all these interpretations about the atmospheric, the physical, all this is kind of like an interpretation of scientists, kind of like trying to make sense for us of what people are saying. No, people will say, "Oh, people are not hunting respectfully," and then the spirit come and it's taking the animals away because it's angry. No, so there were kind of like different culturally grounded explanations. So basically, for this first part, how do indigenous people and local communities experience climate change impacts? Two main ideas I have discussed here is first, indigenous people report numerous, ongoing, tangible, and situated impacts and cascading effects, right? Changes in rain goes down, and this provides this holistic view of change. And then the second idea, main idea for this part, is that indigenous people and local communities recognize climate change as one of many drivers of environmental change, right? They are situated in other many changes. The second question we were looking at is at how indigenous people and local communities respond and adjust to climate change impacts. And here, again, we collected information of all these data, and the question here was okay, what changes have you seen? And when the people told us this change, we say, "Oh, is it affecting you? What have you done because of this change?" Right? And then we kind of like develop, codify different adaptations measures, right? So there were many adaptations strategies. We found that these strategies respond both to environmental and social processes, and many of them are based in adaptations or changes in their livelihoods, right? In their cultivation systems, the livelihood, the fishing, hunting, gathering, aquaculture, right? So these are adaptations that change the relationship with the natural environment. We also found that most of the responses that people have are incrementals, right? And this is kind of like the green, yellow colors, right? Most of the responses that people were telling were adjusting some things, shifting a little bit, or on the crops cultivation, but not transforming radically. Some of the responses, and you see it on the other end of the arrow, require people to completely shift their livelihood or to move outside. These were less reported. But the important point that I want to emphasize here is also that these responses in all the cases were costly to the people. So people have to bear the cost of the adaptation and the change of the relationship with the environment. And other test we did here was like, okay, so we wanted to know whether it's people who are perceiving more changes, no? Like we asked people, okay, what changes did you see? And some people told us less changes, and some people told us many impacts. and we say, okay, so is people who perceiving more impacts acting more, taking more adaptation measurements? And we found that actually that was not the case, right? Not necessarily the people who perceive more changes are adapting. And this was because some of the households have lacked the measures, the adaptive measures. So people who have low adaptive responses actually were the households with fewer assets, low social capital, or limited access to food and water security, right? So it's not the fact that you perceive climate change or impacts that it's going to make you adapt. Sometimes you don't have the capacity to adapt. So again, quickly summarizing the second part on adaptation, our main findings here was that indigenous and local knowledge systems enable these context-specific responses to climate change, but they are dependent on other factors like political factors, economic. The second one was that these responses by indigenous people and local communities are diverse across their livelihoods, but they are always costly. And the last one, this I just mentioned, is these adaptations constraints are diverse, but the ability of households to adapt to take adaptation measurements doesn't depend on their perceptions, but depends on their other assets, no, ownership, social capital, etc. So let me just move quickly to the last part that is on these reflections on the process of weaving local knowledge, climate, and more scientific knowledge. And I think one of the lessons that we had is that the understandings of climate change impacts that come from different knowledge systems do not always overlap. Here, this is an article that we published on the Tuareg in Algeria. And when we were asking people, okay, so what changes have you seen? And many of the changes that people report, actually a big majority of the changes people report, have to do with the annual cycle, right? The rains come later, the birds don't come at the time, etc., right? And this is kind of represented in these circles, the calendar, the switching of activities because of this. I mean, people perceive that there is a switching of activities. And when we compare that with climate data, weather data on this area, we actually found that this was kind of like, there was a match between what people were telling us and the weather data. But some of the changes also have to do with changes in a more linear time, right? Now there are more floods than it used to be in the past. No, 20 years ago there were no rains and no floods, and now there are floods. So people, in this case, they didn't have their perception of the people didn't match with the data from the meteorological stations. So the meteorological stations were kind of like signaling that there were more floodings and more droughts more frequently on time. And people didn't perceive that. No? And again, this is not to kind of like say that who's right or who's wrong, but it's like if people are not perceiving that, they are not even going to be trying to adapt. No, so we need to understand when different knowledge systems match and analyze the differences. Another important reflection that we have in this was this idea that the conceptualizations of climate change of indigenous people are very different from what we say, right? As I say, oh, we're just talking about what's changing. And then I like a lot this quote of this Yanomami leader, David Kopenawa, that he said, oh, for me, climate change is just the revenge of the earth, right? Because they situate themselves in this kind of like more, we have this relationship with the land, with the earth, and because we are not taking care of it, because we are not praying to the gods, it's taking a revenge against that. And it's important, I think, for us that we approach these societies with like a scientific conceptualization to be aware of this and to respect that. Another of the findings, another of the reflections that we have is that, and this has to do also with the funding we have we have funding from this big European project, and this kind of like one of the conditions of this project is that we have to put data on their make data accessible, open science, right? But many of the knowledge that we were using, that we were kind of like analyzing, it was not our knowledge. It was the knowledge of indigenous people and local communities, right? And they have their own protocols, their own traditions on how knowledge should be shared. And when we wanted to kind of like say, okay, so how are we gonna kind of like be able to put the data on the open data, following these principles that it has to be findable, accessible, interoperable, and reusable, how are we going to be merging that with the idea that indigenous people should be able to have the collective benefit, the control, and the responsibility of their data, right? So we found that there was a kind of like a gap, and our current protocols in science do not allow us to do that very well. And the final reflection we have on this project regarding climate change impacts was on the impacts of the actual environmental impacts of our research. At the end of the study, because this was such a big project in 50 sites, flying all over the world, and then we had the COVID, and at some point we said, okay, what are we doing? We're like, kind of like trying to fight climate change and just flying all over the world. So we wanted to kind of like assess the climate, the carbon emissions that we have done the project. And we kind of like published this article in the Journal of Cleaner Production on how much, we emitted like 120 CO2 tons. This is like, I call that my shame slide, because it's kind of like we emitted 120 CO2 tons just for the first part of this project, right? It's huge. And then we kind of like started thinking of ways and we could have reduced that emission with other scenarios, right? So it took us to a whole reflection of like, how are we actually doing research on climate change, actually not really caring of our impact. So yes, my last two slides are about the policy. I said that one of the goals of the Lychee project was to kind of like bring some of these insights to the policy realm. And I think our main conclusion that was this idea that there is a need to recognize indigenous people and local communities as legitimate custodians of knowledge regarding climate change, and honor the right to participate in decision making related to their territory, right? And we kind of like unpack this in kind of like different moments into the policy design project, where you could actually bring indigenous knowledge or indigenous insights from grounding policies in indigenous knowledge, not only in science, to taking into account values, to kind of like funding research that it's kind of like, or projects that where the money goes directly to indigenous people, etc. Right? So, and just to say that we have been, with different members of the Lychee project, have been bringing some of these insights to different kind of like international initiative, the IPBES IPCC workshop, the IPBES transformative change, and then some of the UNESCO kind of like discussions on how to salvagard intangible cultural heritage from climate change, and in this meeting on cultural heritage and climate change. And here are slides with some of the people that have worked in these projects, and this slide of us working online, because as I said, a lot of this happened during COVID. That's it. Thank you.
Thank you. Thank you, Victoria. Great talk. Global coverage using local insights. Great combination. Now we have around 15 minutes to questions from the audience. The idea is that you are gonna, if you have a question, type it on the chat box. I will try to formulate either the same question or putting together different questions, questions from different people about the same topic, so Victoria can answer that. And while you are thinking and preparing your questions, I guess I will kick us off with one question for Vicky. You mentioned the importance of having, assets and social capital and food security to be able to have the adaptive capacity, right? So I was thinking, now we have, and you also mentioned this incremental change. So, but we also see more and more extreme events and sort of like fast-paced changes that might overwhelm the capacity to generate knowledge and to have knowledge for those new events. And at the same time, we have a lot of social economic processes that are sort of dismantling communities and the capacity to generate knowledge. So if we kind of project this to the future a little bit, not even further in the future, where is this capacity going to come from? And is this capacity going to be able to have knowledge to understand these fast changes?
Yeah, well, I mean, no one can foresee the future, right? But I mean, I think one of the important points on this adaptation work that we did is this idea that differently than what happens in our society, our societies, in my country, right, like Spain or the US, where when there are some events like that, governments kind of like act and help villagers or people in some way or another, better or worse, in those communities. And that's what was my point of like, adaptation is costly. No one is helping them to adapt, right? And when changes are subtle, like, okay, I can adapt by changing the time of planting my seeds, that's something that people can assume, right? But when there are like these major events, as you say, there are no kind of like, it's a disaster, right? And there are no capacity to adapt. So I think, and this is, one of the claims of many indigenous groups that working in this kind of like spaces of climate justice, is this idea that these people have generated less of the impacts of climate change and are assuming most of the cost because they are also less protected. They are more vulnerable, right? So well, I think that's a discussion. No, we need to bring these people into the conversation so they are able to tell us how they are being affected, and as society can react to that. I didn't solve your question, but I say something.
We can keep this conversation later, but I want to ask you a question from the audience, from Brita. She wants you to elaborate on how do you solve what she calls the care challenge. How did you realize that the local communities benefited and kept control?
Right. So this is a very interesting. Thank you for asking this question. Actually, so what happened at the project? We designed the project. We say, oh yeah, we're gonna put it in open access, and then eventually we realized that this was not what communities necessarily wanted, or this was not consulted with the communities, right? So at that point, the ERC have a different kind of like funding that it's called the proof of concept funded. So we asked basically for additional funded, and I hire a technician that designed like a whole toolkit, a whole instruments. Our data, it's all the lychee data. It's in a repository that it's called Dataverse. I don't know if some of you are kind of like familiar with that, but this is one of these big repositories where scientists put their data, right? And this is kind of like, okay, so you collect some data and you can just put it there. It's called Dataverse. But if you put it there, it's open. So I have this technician kind of like designing a toolkit that that allows that this data is on the repository but cannot be used unless, I mean, to be used, you need to request the permission of the local communities. So now this is a kind of like package, or computer package that it's installed in the database and that anyone can use. So we kind of like develop this for our project to protect a little bit our people. I mean, the data of the people that trusted us with their data, but it's now kind of like public and it's there. It's not perfect, but it was kind of like a quick reaction and a first step in this idea that we should be more respectful with the data that we have been trusted.
Great, thank you. And I have another question here, and it's about the reception that this work got from different audiences and different groups. You know, is this a question from Don? He imagines that the IPBES and UNESCO are friendly audiences, and what about other authors, actors, and other sectors that might be not that friendly and open to, you know, indigenous knowledge and local communities knowledge?
I mean, I mean, there are people who are obviously accepting of this, but I think that because the project in itself was designed to bridge the kind of like different kind of like conceptual knowledge, we don't, no one is happy, right? Indigenous people might feel that we are not representing their knowledge, and scientists more from the natural science might think that indigenous knowledge doesn't bring anything. But I think because we have been able to kind of like bridge between the two, everyone kind of understand where we are, and we bring something. I haven't had personally many kind of like negative reactions, and more in these audiences where I have presented it in the UNESCO, IPBES, IPCC. It has always been kind of like well received because of this idea that we are bringing one voice or voices that were kind of like separate. Oh, the Inuits here, the Tuareg there, the Chimane there. Now they are kind of like speaking. They are not speaking with one voice. That's not what it is. But we are able to see that there are patterns in what they are saying, and I think that's well received in general, including by indigenous people. Yeah.
I want to build on Don's question, and thinking that this conference is organized as part of the World Meteorological Organization, and a lot of the people in the meeting also comes from the National Meteorological Services. So I wonder if you can think on, let's say, practical ways for these folks from the National Met Services, right? In how to practical ways to bridge or to weave with the indigenous knowledge or the knowledge of their local communities in terms of for their own products, for the National Met Services products, but also in ways of how can we help the National Met offices in sort of like thinking which products can be of better use for the indigenous communities.
In one of the cases with the Chimane, we had like a very interesting study where we look at indigenous knowledge and then local weather data and data from global models, right? So we ask people, okay, does it rain more or less than in the past? No, this question is and then we look at what the local weather stations, which is basically in the airport, in the local airport, no, like a small weather station, is saying, and what the models are saying. And we found that local weather that there was a match between what people were saying and local weather stations, and there was no match between indigenous knowledge and climate models, or between local stations and climate models. And I think this is very important, because the idea of this kind of localized weather, I mean, this enhances this idea that there is a value on these local kind of like climatological stations, not the ones that I was showing in this initial map that are only kind of like some of them that have longer records. And I think that emphasize this idea that many of the things have to be measured locally to make sense, because people don't, I mean, not to say that global models are not useful, but they are useful for global things, right? But when you are talking about adaptations or local kind of like responses, it has to be with local data. And that's where these more local weather stations have a value.
I have another question here, and I think this is an easy one, is what is next for the Lychee project? Where are you guys taking this?
So we have kind of like this, I mean, we keep analyzing the data, and we have all these requests of people that want to add data to the Lychee project. But I don't know, my hope was that someone will take this and continue, right, with it. And this was the idea of creating the network. But so far, maybe whoever asked this question want to take the Lychee project. The
Okay.
network is there.
Oh yeah. Okay. No, that's good to know. Yeah, and it can be interesting to think about in the continuity of the project, right? And maybe a more decentralized effort and
Exactly.
yeah. Okay. And I imagine it's not very cheap also, so we'll need some funding, right? I don't know if I have more questions. I don't see any more questions. Don, do you see them in the?
Yeah,
One
Pamela has a
just came
question
up.
that is in there, Julio.
I don't.
Okay.
Can you read
So
it, please?
I can take care of it then. So this it says I want to support Victoria with a case in Kenya where participatory scenario planning has provided evidence of indigenous communities and meteorological products and how they complement. So Pamela, yeah.
Sure, I mean, just write to me. My email was, I think it was on the slide. It's very amazing to find in the internet.
Julio, do you see coming in from Elizabeth?
Oh yes, yeah. The chat has multiple windows. I realize this. Yeah, I think it's something that you touched upon earlier, Vicky. Is Elizabeth is asking at what point in the knowledge or perceptions of indigenous communities is introduced into the bridge of interaction between science and indigenous communities.
Yeah, so what we did was to collect observations, right? People were telling us, okay, what do you see? And I think the bridge is done with this kind of, well, the first bridge is kind of like this local peer review. So we ask people to verify that what other people are saying it's true, to have like this site observation, and then translating these local observations into the Lychee tree, right? Into the kind of like quantifiable kind of like method that we design. And that's where kind of like you can say, for example, now we are doing another analysis of this data and looking at the water cycle, right? What are the processes that people perceive as changing? Is it evaporation? Because all these observations, I mean, all these indicators, you can then kind of like reclassify, no? Is rain, what does it refer? It refers to precipitation. And then the soil is dry, this is referring to evaporation, right? So you can bring these local observations to the language of the scientists once you have it coded on the Lychee tree. So I think that's what allowed us to make the bridge between what local people say and what scientists kind of like work with.
Great, thank you. And I'm gonna close with one final question that I don't think it's that easy. How do you guys, you're working in this sort of like interface, right? In different multiple knowledge systems. And I often hear that there is power relations and power asymmetries into those. And we can say, okay, Western positive science is the most powerful in those systems. How do you navigate those asymmetries, and how do you overcome those asymmetries in a way to try to weave multiple knowledge systems in a productive, constructive way?
Yeah, that's, I mean, it is really an issue. One of the ways we try, or I tried it was in the design of the projects. So from the start, of all these 50 Litchi partners, many of them are kind of like from their local communities. They are from NGOs. Some of them are PhD students or postdocs, but I always selected people with long-term relationships with the communities that they work with, or people from NGOs or working in the communities. This doesn't kind of like remove power relations, but it gave me like the assurance that there was some trust in the between the person in charge of like collecting the data and the community, right? I didn't want to impose in a sense, but to work with people that work respectfully, and this is with the communities. And this is one of the reasons why with the COVID, some of the sites we have to look for other sites, right? Because some people say, no, I cannot go to that community in this moment, and because there was like this kind of like collaborative relation. So yeah, I don't think this removed that, but my take is work with people that respect the processes, right? And yeah.
Okay, with that, I want to close the session, and not before thanking tremendously Victoria for giving us the opportunity to benefit from her great work and taking the time on her sabbatical to spend time with us. You know, she's in the middle of the mountains, enjoying the landscape and working very hard. So thank you, Vicky, for sharing your knowledge with us. We're extremely excited, and hope you can stay a little bit longer for the other talks coming. So let's give it a round of applause to Victoria.
Thank you. Thank you.
And
thank you for the invitation. Yeah.
You're very welcome. Now we have the next talk is by Tobias Geiger, and after him is going to be Britta Hollerman. Do we have Tobias?
Yes, I am here.
Hi,
good
Tobias.
evening. Good evening, everyone. Or from Potsdam in Germany. At least it's evening here. I'm just looking for my screen to share. Let me try this one. I try to share the full screen and check if you see my slides now.
Okay, perfect. So we have Tobias Geiger. I'm sorry for my mispronunciation. He comes from the German Meteorological Service at Potsdam in Germany. Tobias, you have around 12, 14 minutes. Please.
Thank you very much. I'll give my best. So yeah, this is work with some colleagues from the German Met Service, but also from the ETH Zurich and the Potsdam Institute for Climate Impact Research. And the goal was to bridge seasonal climate predictions and impact models for operational risk assessment. And just let me give you a quick overview. So in order to pick up all the listeners here, I want to talk about what are seasonal predictions in general, and why do we need, I think, seasonal impact prediction. And then I will talk about a risk modeling framework, Climata, and the new forecast tools that we developed for that. And I will give a short example of the application that we do in Germany before I summarize. So let me start with this slide. So the goal is to make seasonal prediction more useful. And this famous graphic, which has been shown at various instances, somehow explains how the value chain of weather and climate services looks. And most of the time, I see this graphic being used for weather services. So really like the next week to 10 days of forecasting just weather. And I am working in the climate part of the German Weather Service, and we are looking at climate services. And from my work, I see that this chain basically is, applies to the climate part as well. So that's why we kind of adapted this chain a little bit. And the goal is here to make climate services more useful and for society, and that might not be leading to warnings, as you know, for weather warnings, but that might be different forms of risk communications and decision support that might be useful for other types of actors. And the idea here is to use that impact forecasting mountain in the middle and combine that with seasonal prediction systems to provide climate risk assessments for decision making. But before I dive deeper into it, let me spend a few moments on telling you what are seasonal predictions and why they are useful in general. So seasonal predictions are basically a climate forecast over the next several months. And this is different from a weather forecast. It usually doesn't provide like the weather in 3 months ahead of time, but it usually provides statistical values, 3 months mean values as anomalies from a reference period. So is it warmer or colder than it has been in the last 30 years on average, for example? And usually these values are provided for mean temperature, amount of precipitation over 3 months, and then you create maps like that on the right. So that is the actual forecast of the DWD system for Europe. And then you see, okay, on average, it might be slightly warmer in the next 3 months than it has been over the last 30 years. And then you have some patterns, and then you have some skill. So the seasonal forecast is usually passed on with a skill. And basically, it's on the map here, it's the size of the circles. Larger circles means high skill, smaller circles less skill. So can you trust the information that is provided? Can you use that information to make decisions? And at the German Met Service and other Met services, we usually have users like hydrological modelers from the agriculture sector, energy sector, that are people that can actually digest this information, this 3 months averages into their models and make some prediction. And the goal here is to go on and try to check if we can provide other measures that are useful for other types of actors and even for the public maybe. And the next part in this, of course, is if we want to make a seasonal impact prediction and not just a seasonal prediction, we need an impact model. And at DWD, we are using the Python framework Climata, which is an impact modeling framework in a IPCC propeller sense. So you have 3 contributions. You have a weather hazard contribution, you have an exposure contribution, and you have a vulnerability contribution, for example, a damage function that then can be combined to define a risk or impacts or some sort of damages. And this tool is nice because it's open source available on GitHub. It's constantly developed and managed by colleagues from ETH Zurich, but also from other other people, scientists, and also partly from other meteorological service providers. And it has very extensive tutorials, multiple use cases available. So it's very handy to start with something like that. And then in the end, this tool allows you to provide risk analyses and impact warnings, etc. So it applies for the weather scale as well as for the climate scale. And the idea is here now to bring this seasonal forecast system. We will rely here on the climate data store by the Copernicus as a provider, since the project was also funded by Copernicus, and combine this basically chain in order to with the Climata impact modeling framework to provide seasonal impact forecasts. And we have been doing this in developing a new package for Climata, which is called the Climata Seasonal Forecast package. And I don't have so much time to basically walk you through the whole package. And otherwise I would have done a live presentation of how you can run it. But I just want to point you to two sites. So that's the Google Colab demonstrator, where the Jupyter Notebook of this tool is actually can be directly used. You don't need to install anything. You can basically use it online and try to get your first seasonal forecast impact calculation done. And then there's also the documentation of Climata, where the full package is described and it's told how you can use it. Just let me quickly walk you through the features. What can the tool do? It allows you basically to start from the Copernicus data store, download any seasonal forecast that is published there. This is from different meteorological agencies worldwide. And then it allows you to process the raw data and generate climate indices. For the project, we focused on heat, on temperature-based indicators, since they have the most skill, but for other reasons as well. And there's a list of indicators that basically can be generated with the package immediately out of the seasonal forecast. And then you can create so-called hazard objects in Climata that basically the next step then of doing an impact calculation. I just show some screenshots that are basically come out of the documentation. Here we have selected the DWD model, selected Uruguay as a case study, and then you see an ensemble of 50 member seasonal forecasts, and then you can basically extract temperature information for a single day, temperature information for a period. You can also do statistics for different forecast months and look at the spread of the ensemble and try to work with the data. So it's all there if you want to start. And before I now end up, I want to tell you a little bit about a project that is still ongoing when we're trying to use that toolbox now to provide or to develop operational seasonal impact prediction at the German Weather Service. And the idea is here that we have realized, or we have a project that looks into labor market effects and weather or climate effects. So what do we see? What are some weather patterns that affect the labor market? And one thing that we see in Germany is there's some sort of short time work allowances. So if a company cannot work because of bad weather, they get allowance from the German government. So some fraction of the salary of the workers is paid by the German government. So the workers are not basically fired. They can stay in the company, and once the weather gets better, they start working again. And this is of course very costly for the German government. And the question is, can we basically ahead of time, using seasonal prediction, predict some sort of impact of the costs that are expected? And with colleagues from the economics sector, we have conducted a retrospective analysis of this short-term work allowances, and basically we created a dashboard. You can look at the data. So here's an example for the construction sector in winter, and what one sees here, if the winter is warmer than expected, then basically the amount of allowance for short-time work goes down. So it's cheaper for the government because the work can continue as you might expect. So this is a robust signal that we see across Germany. And now we are in the stage of basically getting this retrospective information into a forecast system where we select the heat indicator for Germany that is most predictive of this this amount of allowance that needs to be paid out. And we also check if there's skill in this forecast, which is really important. Otherwise, it doesn't make sense to use that indicator. And then in the end, you can make an impact prediction out of that. So this was a rough tour through the work that we have been doing. And let me summarize. So the first step really is seasonal prediction beyond mean values is skillful, can be used, and we have been looking at unusual temperatures, heat extremes, and see that there's some skill. We do have operational heat extreme forecasts for seasonal prediction available at the German Weather Service, and within the project, then we have basically combined this seasonal prediction with an impact model, namely Climada, and have created that tool. And so we are currently working on providing operational seasonal impact prediction. And since the tool is freely available, everyone else is invited to do so as well. Thank you very much for your attention.
Thank you, Tobias. Sorry for.
It's both fine. Thanks.
Oh, perfect. Okay, thank you. Thank you for the talk. We have a couple of minutes for questions. I don't see any questions, but I have a sort of like a operational question. What are sort of like the technical needs that you need for this to produce what you call skillful models, right? Do you need a very dense network of met stations, or not so much? What is the scale, or what is the resolution that your models are getting?
It depends a little bit on the case, but these seasonal predictions are regularly produced by many service providers, meteorological service providers, and they are uploaded at the Copernicus data store. So everyone can basically use them and check now with the tool if that is relevant information for them. And of course, there are subtleties involved, and that is not if you want to go operational, there are many other questions that you have to deal with. But in general, it allows to go the whole way, and then you have to check what comes out in the end. But if anyone has questions regarding that, please get in contact.
Perfect. Thank you. Thank you very much. There's a question from Mahiel, is whether you are looking at this forecast can be very relevant for tourism and recreation and hospitality sectors. Are these sectors that you are looking at?
Yeah, they also pop up. So in the dashboard, we also look at hospitality and recreation. And yeah, I have to check now myself. But of course, this is relevant information. If you somehow have an impression you get a warm winter and for example, and recreational winter vacation in the Alps or whatever is not possible, then you might I don't know, think about how many people you would employ in your business to run winter recreation, or if you would do something else. So yeah.
Perfect. Thank you very much again. And
Thank
now we're moving into the next presenter, Britta Hollermann. Again, apologies for my multiple mispronunciations. This is going to be a topic
Very fine, thank you.
And are you able to share your screen? Do you have the power?
Yes, I think so.
Well, if not, Katie can give you the power. She is the most powerful person in the session. She just grants
just
power
give me
at
a
her
hand
will.
if it's
Perfect. Yes, so we have Britta Hollermann from the Osnabrück University in Germany, and she's gonna tell us how uncertainty shapes what we do or what we don't do when there's some risks related to floods. Britta, take it away.
Yeah, good evening to everybody, and thank you for this kind introduction. So today I would like to introduce you to the uncertainty lens framework I developed with my colleague Anna Heidenreich. And we want to explain, or this uncertainty lens framework can explain why high quality hazard information and forecast often fail to translate into protective action. And the core idea is that people do not respond to forecasts as data processors, but as social actors who interpret warnings to prior experience, routines, institutional expectations, and cognitive shortcuts. And we developed the framework using a severe flooding in Germany, the 2021 Our Valley flood, as an empirical case. You can see the one picture of that flood here presented. So is it the next slide? Yeah. So yeah, as I just mentioned, there is still a gap between the technical forecast and the effective response, even though the forecast significantly improved, and that was also the case in the 2021 flood. So just have a look at the flood markers at that house, which we can see on that building. What do people think if they receive a flood warning and they have this in mind? What would you think? Well, you see what popped up. Oh, and I can see Julio, yeah, surprised. I was too. And so there are floods beyond known limits, which has implications for warnings that uncertainty needs to be part of the information. And if it's not acknowledged and contextualized, people fill the gap with fast judgments. Sometimes they may be adaptive and sometimes they're dangerously not. So up to now, the role of uncertainty perception and how individuals and institutions interpret and respond to ambiguous or incomplete information remains comparatively underexplored. So we think we need to go beyond framing uncertainty as a problem to be overcome and instead highlight its role in shaping decision-making and producing also divergent responses under comparable conditions. And if we want better preparedness and response, we need approaches that treat interpretation and action as the main bottleneck. Yeah, this newspaper article reflects this bottleneck. We can read here that the R reached record level and that the firefighter has not yet experienced such an increase in water level. So if you see when I highlight when it was published in 2016. So when you remember the picture before, the flood, which was very low compared to the 21 flood. And if you, so when you see this difference from that time, 2026, this was a really severe and extraordinary event. And this can be explained with cognitive heuristics. Heuristics are shortcuts for making decisions quickly. And there are two types. Heuristics you want to highlight in this talk. So anchoring. Anchoring means people fixate on familiar reference points. For example, it usually doesn't rain much here, or it's only heavy rain, not a flood. And the other one, the availability bias, says, or people overweight what they can easily recall. So maybe the last flood. So prior near misses or mild outcomes become a mental template, even when the present signals do not fit. So the uncomfortable implication here is better numbers alone can still feed the wrong heuristics if they do not reshape the reference points people use. And there are two established explanations in the literature that can help, but each leaves a gap when used alone. So on the one side, we have on the community side, the safe development paradox, which explains how protection can unintentionally stimulate exposure. And on the individual side, we have the protection motivation theory, which explains how people decide to protect themselves based on threat appraisal and coping appraisal. The problem is that the safe development paradox is strong on long-term socio-technical dynamics and on the community level, while the PMT is strong on individual behavior. And our contribution is here to connect these levels to the way uncertainty is perceived and managed, and how uncertainty perception drives the sense of safety and the response action. Let me briefly explain the safe development paradox. So in the first loop, you see in the upper part of the picture, it measures successfully. Measures successfully reduce frequent losses, like dikes or floodplains. However, less flood events may encourage activities in the floodplains, and societies become more vulnerable to rare events. And this is seen in the lower loop. When an extreme event exceeds the protection level, so this is a little bit indicated with the equal sign, then the damage can be higher, precisely because the system has encouraged and normalized the belief that we are protected. And the key point here is that not protection is bad, it is that safety and sense of safety are not the same variable. So let's dig deeper. So safety and the sense of safety are influenced by known flood protection measures and or weather and flood forecasts. And these are the source of information people use to make decisions by assessing their threat, ownership, and coping appraisal. For this, they ask themselves, am I sufficient at risk to worry about? This would be the threat appraisal. Is it my responsibility to take action? That would be the ownership appraisal. We extended here, or we used an extension of the original protection motivation theory because we find this ownership appraisal quite important. And the last question addressing the coping appraisal is, can I take effective action that is affordable? And the uncertainty lens, this sits between these two. It describes how institutional conditions on the one side and individual competencies on the other side shape the way uncertainty is interpreted, and therefore whether appraisals lead to protective or non-protective action. So I now present the uncertainty lens framework I already triggered. The lower part of the figure represents the protection motivation logic that I just explained. The three appraisals are influenced by uncertainty perception and are further mediated by the uncertainty setting. This is the setting the individual is exposed to, which includes known policies, trust in institutions, and perceived responsibilities. And it is further mediated by the individual's uncertainty competencies, which are based on experience, capabilities, attitudes, and routines. Under pressure, people use cognitive shortcuts, as I just mentioned, anchors and availabilities, which then shape the three appraisals. So then it can happen that these shortcuts are not supportive and misleading, turning the decision into a maladaptive outcome. And this shows that uncertainty is not just received, but socially organized and personally processed. To empirically ground our conceptual framework, we mapped expressions of uncertainty of flood-affected people and how it influenced their coping response. We used the Aral Valley flood in 2021. We used complementary data sources, newspaper corpus, and household surveys. We analyzed the direct and indirect flows there. We coded everything, and we analyzed the expressions, the uncertainty expressions via content analysis in relation to the heuristics I just mentioned and the framework elements. The results show how the uncertainty setting and competence influence the assessment. So while some people rely too much on external information, there's also skepticism here. This can be seen in the interplay between over-reliance on existing flood warnings and the simultaneous perception that warnings are unreliable. So the quote says, the large number of severe weather warnings contributed significantly to the fact that the warnings in the run-up to the 14th July were not heeded to the necessary extent. So here, trust and knowledge about assigned responsibilities as part of the uncertainty setting are important. Regarding the uncertainty competence, many respondents emphasize limits of lived experience. It has never rained this much here before, or the belief that the place is inherently safe because it's perceived as idyllic. Besides previous experiences, also attitudes come into play. So looking at the three appraisals, regarding the threat appraisals, quotes show a disbelief and spatial misinterpretation. People could not imagine these volumes which came down on that night. They interpreted distance warnings as granted or reassured themselves by remembering the absence of last flooding in their house. If it comes to the ownership appraisal, we can see frustration about how the warning was communicated and that the received warnings were not perceived as such, since actionable translation and clear to-dos were missing. This directly leads to coping appraisal, where numeric information often fail to trigger meaning. even for respondents who describe themselves as numbers people. A value like 200 liters per square can be technically alarming and at the same time psychologically inert. So furthermore, past successful dealing with floods lead to overestimation of coping capacity. The strong belief that it won't get worse triggered inaction. Thus, uncertainty is not only in the forecast perception, it is in the mapping from the forecast perception to responsibility and from responsibility to a concrete next step. So overall, 3 safety illusions emerge from these findings. It stems from past experience. We have seen floods before, delegated roles, someone else is in charge, and institutional trust. The system must or will protect us. These illusions are reinforced by cognitive heuristics when dealing with uncertainty. Against this background, the science policy endeavor to increase confidence in future risk assessment needs to acknowledge residual uncertainties. Otherwise, it bears the risk of further unintended consequences or harmful coping responses. So here our framework can support in identifying subjective uncertainty. Furthermore, by exploring uncertainty settings and the underlying feedbacks between individual and community levels, may support in increasing flood literacy. And to conclude, the practical implication could be to raise awareness that there is no certainty, even with measures and warnings, and to treat that as a design constraint rather than a communication problem. And preparedness improves when people have practical anchors for scenarios that exceed imagination, and that those are reset after near-miss event. And risk decisions should be treated as socially and institutionally embedded, meaning uncertainty communication must be linked to roles, practices, and sustained community engagement. So we are in this session. So to achieve this, we strongly believe we need a co-creative and transdisciplinary approach, which explicitly addresses uncertainty and engage citizens. This will address the aforementioned bottleneck and support that future warnings are interpreted in the context of shared mental models, established trustful relationships, and preparedness measures. Thank you.
Thank you, Brita. I'll go ahead and pick up for Julio as we wrap up this session. There are 2 questions in the chat, but for the sake of time, I'll start with the first, and then we can move into our short break. So here we have one asking about the communication gap, the uncertainty, not aligning with the procedures of stakeholders, ultimately leading to this communication gap. What you were saying also being parallel to a perspective from Luxembourg. Do you believe that this perception bias and late action are broader than the governance and emergency response levels? And if you need more clarification on that, please let me know.
Yeah, I'm thinking about that.
Yes.
I didn't hear that talk from Jeff, so that's hard to answer that. Does it mean that uncertainty doesn't that the procedures? I think it's not so much about the stakeholders. You could look at the stakeholders and the politicians who make the decisions and then trigger a warning or say that there must be an evacuation. What we were looking at was about the individuals who were original receivers of evacuation calls, of evacuate the 50 meter of the river, and then what they see when there is no rain, for example, and they hear such a warning that say, "Well, it's not raining at all. Why should I do something?" And that these people learn to cope and navigate this uncertainty that it must be no rain to get a flood, for example. So it's a lack of knowledge, and it's and this is part of this uncertainty and how to deal with it. I think this might be a little bit different what Philippe meant with his question, but maybe we can talk later in the chat about that.
That sounds great. And at this point, thank you so much, Brita, for your talk. We'll go ahead and take a 15-minute break approximately, so really 13-minute break, and begin again shortly at 20:45 UTC time. So I will see you all back here in approximately 13 minutes, and we'll start the rest of the session. So any further questions can be placed in the chat, and speakers are welcome to address them there. Thank you so much. We'll see you shortly. All right, everyone, we are about to get started with our second group of talks for today. And before we begin, I wanted to give some quick reminders for those who have been joining us throughout the session. If you are participating, please keep your microphone off. And participants, you're welcome to put your questions in the chat throughout the talk, and those will be read by the moderator, myself, for this block. This will allow us to try to combine similar questions if possible, and then if there's not time to get through every question, the speaker can answer them in writing as well. Speakers, please try to keep your talks to around 12 to 14 minutes. If we're approaching the 14-minute mark, I will give a quick 1-minute reminder. And with that, we can go ahead and get started. So our next talk is by Joanne Robbins from the Exeter Met Office in the United Kingdom. And Joanne, you should be able to share your screen. Joanne's talk is on impact-based warnings, aligning methodological choice with warning purpose.
Thanks, Katie. Hopefully you can see my slides, and they should be coming through in slideshow mode now. Has that worked?
This is in presentation mode, so maybe try duplicate.
Okay, 1 second. Zoom is a strange one for me. Let me just see if I can swap screen. And then I'll swap you over here. Hopefully this will work. Can you see my screen now? Oh, I can. There we go. Right. Hopefully that will now be working. Is that working?
Yes.
Perfect. Sorry, just faff around with the screens. So, thank you very much for the introduction. Sorry for the mild technical hitch there at the beginning. So yes, my talk this evening is going to be around impact-based warnings and aligning methodological choice with the warning purpose. I'd like to thank my colleagues Sally Potter, Sarah Harrison, Faye Nielsen and Richard Turner, who have all provided fantastic insights to deliver on this work. This is going to focus on the UK, but our project actually has a broader remit, which includes looking at New Zealand as a case study as well. But as I say, this will focus very much on the UK results. So why is it important that we consider methodological choice in impact-based forecasting? Well, at the moment, impact-based forecasting and warning tends to represent an umbrella. And under that, there are a lot of different methodologies that are being applied. So the schematic on the side of this slide, it's basically illustrating from some work we did with semi-structured interviews how different people around the globe are trying to implement impact-based forecasting. And this can start from some sort of hazard-centric forecasts. It can move into forecasts which are looking at how do we include vulnerability and exposure data to provide more risk-based approach, all the way through to quantitative impact modelling and multi-hazard, multi-impact modelling types. And as one might expect, as you go through this, you grow with complexity, but also the capacity and governance needs. And so really what we're saying here is that there are lots of different approaches that could be appropriate. And it's interesting when we then start to reflect on how many of these are addressing critical purposes that these warnings need to offer. So current IBFW guidance recognises the importance of including vulnerability and exposure data, but I think it's fair to say that guidance on what is considered optimal and meets specifically the needs or the purpose of these warnings is perhaps less well documented. And I think one of the things I consistently see when I go to conferences is this question of what are we actually including when we say we're putting in vulnerability and exposure data, and are we adequately considering the influence these data sets have on warning issuance? So the work that we're doing here is really aiming to address that question. So just to give a bit of background, hopefully I think everybody on this call will obviously kind of know this, but when we're talking about vulnerabilities, we're really looking at elements that can increase susceptibility of an individual, a community, an asset or a system to the impacts of a hazard, while the exposure is the tangible human assets that are located in hazard-prone areas. Obviously, these can be expanded or reduced depending on the specific warning that you want to provide. They can be quantitative or they can be proxy data sets. So there's a lot of variability in what these actually represent in a data context. On the left-hand side, I've illustrated that within the UK context, we have a number of decision support tools, two of which are illustrated here, which are hazard impact models, which aim to address this from an automated decision support perspective. And so they automatically include elements of hazard, very much from an ensemble forecasting perspective. And then they also look to include vulnerability and exposure components through different mechanisms. So in the surface water flooding context, we're utilising flood maps, as well as national receptor databases and national population databases to convey what vulnerability and exposure might be. While in the wind hazard impact model, and specifically looking at transport sector, we have to utilise data in a slightly different way because we're looking at a cascade of potential impacts. But we're still interested in different vulnerabilities. So in this particular case, we were looking at how many vehicles would be blown over associated with a particular wind event. And in that regard, the sort of vulnerabilities on the road network are things like, are you in a bridge or are you on a tunnel? How high is that road relative to the rest of the road? And also speaking to resilience a little bit, how many lanes are there on that road? And does that really cover an ability to continue travel, or is it a complete diversion from that road network? And then in the context of what are the exposed elements, this actually has a dual purpose in our case, because we're looking at different types of vehicles and how much goods they may or may not be carrying, because that affects the weight of the vehicle. So it's also interesting to note that vulnerabilities and exposures can have different contexts and different perceptions depending on how you're using them in the model. So again, the question I think we were trying to ask is, what does the inclusion of these data and how you interpret them as the modeler determine how that aligns to the purpose? And how does that mean differences might be seen by people receiving warnings? So we decided to set this up as an experiment, and I will very clearly at the outset say the results here are illustrative. They are not aimed to be comparative to actual warnings that have been issued, and they're not aimed to be exhaustive. So they're really here just to explore the variation rather than be accurate and particularly precise. But the particular thing we wanted to do was look at, well, how does integrating exposure and vulnerability affect who could receive different types of warnings, so different severities of warnings in the impact-based context? Tobias talked about Climada earlier. We chose to use Riskscape. This is a software package that was made in New Zealand, and my colleagues Sarah Harrison and Sally Potter will touch on this more later. But we wanted to use that software as a way to ensure that we had consistency between our two projects. So me in the UK context and them in the New Zealand context. And it just meant that we had very similar processing workflows when we were running the experiments. So experiment 1 focuses on a hazard-only approach. In this context, we're focusing on just a wind hazard event, and we'll go into the data that was used in more detail in the next section, but effectively we use a maximum wind gust scenario for this particular experiment. Experiment 2 then looks at hazard plus exposure data. And in this context, we wanted to focus on buildings and the possibility of building damage triggered by that wind event. And then experiment 3 was what we would call a full risk assessment, in the sense that it took hazard, exposure, and vulnerability, and we used a damage function to do this. The damage function represents how different buildings with different construction materials and ages would respond to different intensities of wind gust speed. And so we're really trying here to incorporate that vulnerability and exposure element. In order to run this experiment, we wanted to use a live case. And so we used an event that happened in February 2022. It was Storm Eunice. This was a particularly interesting case for us in the fact that the storm underwent rapid cyclogenesis. And so predictions related to this event were quite challenging. It was an around 1 in 10-year event, and there were significant impacts across a range of different assets, including the power network, transport, and also we had school closures and significant disruption to medical services. It was actually also a storm that fell between 2 other storms. So we had Storm Dudley first, then Storm Eunice, and then Storm Franklin. And in Storm Eunice, we issued 2 rare red warnings for wind. And these are shown in the bottom of the plot. As I said before going further, we're not trying to compare our outputs to these warnings. We really just wanted to look and explore the differences between a hazard-only approach, a hazard and exposure approach, and a full risk assessment approach, and really understand that variability. So these were the results from experiment 1. So this was a hazard-only approach. So this is just using a maximum wind gust on a single day for the storm event itself. We've used wind gust thresholds, which are used in another decision support tool within the Met Office. So we haven't deviated or used anything differently than we might consider for other automated decision support tools. But what's important to note here is that everybody in southern England would have received some level of warning. And so 79% of the areas would have received an orange, or as we refer to it, an amber warning level, and 14% of areas would have received a red warning. And as you can see from this, the highest gusts were particularly seen around coastal areas, which is to be expected. And then it was slightly less intense as you moved inland, although there are some areas which had localized high gust intensities. So this was just looking at hazard only and applying the thresholds as shown at the top, which again, as I say, are representative of other tools we use at the Met Office. Now, when it came to including exposure data, we were interested in comparing between buildings and population. Now, we were obviously initially interested in how wind impacted buildings specifically, but obviously when you're issuing a warning, you're not issuing a warning to the building, you're issuing the warning to people who live in the buildings or work in the buildings. So both of these data sets have potential to be valuable as the exposed element. But as you can see from the two plots, they show very, very different results. So when you're using building exposure thresholds, which are on the left-hand side of this diagram, 28% of areas would no longer receive a warning. And that equates to around about 6.9 million people in this area. When you then look across to the population, you see a vastly different spatial representation of warning distribution. And actually, in this particular instance, using population exposure thresholds, 50% of areas would no longer have received a warning. And this equates to roughly 10.3 million people. Now, it was interesting when we came to do this because there wasn't actually an easy-to-hand hazard exposure matrix that we could lean on. So we did have to develop thresholds ourselves, and we did it through a data-driven approach. And we believe that the huge differences we see in these two outputs is related to the distribution of the data and also the administrative aggregation areas that we've used. And these are the results from experiment 3. So again, vastly different again. We get a very homogeneous picture, basically yellow across the board. This is because about 40% of the buildings that were modelled actually would have received no damage in this storm. And this is primarily because the major construction material type is brick, block or stone in the UK under masonry construction. So they're actually very well insulated from strong wind events. So we see a huge difference once again. So just in terms of concluding remarks, one thing I would just like to say is that I very quickly tried to get Google AI, given that I think on Thursday we're going to be talking about AI, to tell me what the purpose of an impact-based warning is. And it came up with this: so actionable, timely information that helps the public, authorities and emergency managers prepare for and reduce risks to lives, livelihoods and property, which is great. But in the context of using exposure and vulnerability data, what should we use for that? And what spatial aggregation should we be using that's appropriate? Thank you, Katie. Which thresholds appropriate and how should we decide on these? Who and what is at risk and what needs to be communicated? Is it the people that we want to talk to, but do we want to communicate how they might be impacted? So as I say, buildings being damaged, flying debris that people can avoid. And therefore what needs to be communicated and what needs to be assessed. How does known behaviour response to different warnings influence methodological choice? So for example, looking at the risk outputs in the plot on the right hand side, about 92% of the people in southern England would have received a yellow warning. We know that yellow warnings tend to receive less direct action from them compared to red, or amber. So do we want to consider whether that has an influence? And then lastly, how do we want to verify it? So if we want to verify a warning based on actual impacts that occurred, do we want to actually say, well, we're talking only about buildings and therefore we want to assess whether buildings have been damaged? Or do we want to convey whether it's more to do with did people take the right types of action? So what I'd really like to highlight here is that there's no right or wrong approach necessarily with anything that we've done here, but we do need to very carefully consider the integration strategies required based on what the purpose of that warning should be. And so this is just a highlight of some of the work that we've done. So thank you very much.
Thank you so much for that. For the sake of the schedule, we're going to go ahead and move into our next speaker. So anyone with questions, please go ahead and put them in the chat and Joanne can address them there. Our next speaker is Laura Lucer from the World Bank Group of the United States, who will be speaking presenting a talk called Bridging Science, Governance, and Local Realities, Advancing Early Warning Systems in Fragile Conflict and Violence-Affected Settings. So Laura, the floor is yours.
Hi, everyone. Can you hear me and can you see my screen?
We can hear you loud and clear. The screen is
Okay.
visible. It just needs to be in presentation mode. And there it is.
Is it now? Yes. Okay, perfect. Good evening, everyone. So my name is Laura. I work, as was mentioned, at the Global Facility for Disaster Reduction and Recovery at the World Bank Group. I've been focusing over the past years on me and my team on trying to support countries to make early warning systems work better, specifically in countries that are affected by conflict, violence, or even just fragility. So today I want to discuss this and discuss a reality that we see across those environments, which is that hazard forecasts often exist, even if they're imperfect. However, warnings don't, or they're not acted upon. So the work I will share is based on a white paper that we wrote a few years ago called Early Warning Systems in FCV Settings. And it's drawing from cases from all around the world, but more specifically Haiti, Nigeria, Bangladesh, and Yemen. So over the last decade, med science has really delivered extraordinary improvements in hazard detection, satellite monitoring, numerical weather prediction modeling, and even in the most challenging contexts, we see that some level of forecast data exists, even if it's just coming from regional centers, global models, or remote sensing. However, what we see in those environments is that there's a systematic widening of the usability gap. So the forecast chain, which starts from production, interpretation, dissemination, and early action, becomes more and more brittle. And in FCV settings, so fragile conflict and violence affected settings, this chain is breaking even earlier and more often. And that's not because the science is weak, it's really because the systems that carry the science, so the institutions, communication infrastructures, dissemination pathways, and so on, are fragile, fragmented, disrupted. So really our primary challenge in countries that are affected by fragility or conflict, it's not just forecast availability, but it's really the integrity of the system that will translate those forecasts into actionable warnings. We analyzed dozens of contexts, and we've identified three distinct FCV failure modes that each require different operational strategies. So the first one will be, fragile contexts where you have institutions that exist, but where government capacity is weak, where you probably have partial dissemination coverage, and often forecasting and interpretation capacity is inconsistent. You also have often very limited resources. The second category will be countries experiencing low to medium intensity conflict. We also put in this category countries that have kind of some form of stability, but may be affected by conflict in only part of their, only one region or sub-region of the country. So here you have state authority, which is fragmented and very often. Warning trust is also fractured, and this is very important. And messages may not cross conflict lines. And the final category is the high intensity conflict one, where main issues are that communication systems often break down. You have infrastructure collapse. National institutions may be non-functional at all. And warnings, if they exist, they often need to rely almost entirely on non-state pathways. So across all those three cases, I think there is one consistent lesson, which is that early warning systems need to be redundant, distributed, multi-actor operational nodes. And I know this is true for all contexts, but I think it's even more true in countries that are affected by fragility and conflict. Moving on and coming back to the topic of our conference today, on transdisciplinary approaches. I think for us, it's really important to remind ourselves that it's not something that is nice to have, especially in what we call FCV countries. It's actually a functional requirement. So in this context, we have 4 systems that need to interact for warnings to work. So first you have the scientific systems with the meteorological and hydrological agencies, the regional centers, global models. You also have the institutional systems, the governance part, so DRM agencies, alerting authorities, governance frameworks. You have what we'll call the intermediary systems for dissemination. Media is one of them, but also humanitarian actors, civil society, and so on. And finally, you have local systems that are often the hardest, at least for us from a development and financing institution point of view, that are often the hardest to reach and to interact with. So those are, for instance, community leaders, informal networks, social cohesion structures. And all of those really need to interact, and they need not to act as a linear chain, but rather as a multi-system interface. I'll give 2 contrasting and concrete examples from our work. The first one in Bangladesh, where you have forecasting centers that are highly capable. However, warnings, and this we've been working a lot with the authorities, warnings actually only become usable through a network of over 60,000 volunteers, community radios, megaphones, mosque loudspeakers, and so on. So here you really see how science and community networks need to be bridged so that there can be early action. Another example I wanted to cite is in Yemen. So a typical case of a high intensity conflict and state collapse, where you have forecasting capability that is extremely low at the national level. However, you do have global models and satellite platforms that can help with forecast, but national institutions are disrupted. And dissemination here depends often on humanitarian coordination mechanisms, WhatsApp groups that are operated by civil society, local radio, but also, and I think this is something that is more difficult for us to work on, but also the involvement of non-state actors, including sometimes insurgent groups that control portions of the territory. In more practical terms, and what we're trying to apply in our operations, our research highlighted the importance of this dual track approach that require actually entirely different skill sets. So the first track is important to keep working on strengthening on the longer term, the formal systems. So keep working on observation networks, on the capacity of the Met agencies, on institutional coordination, on forecasting and alerting protocols. So those investments are essential, but they're slow, they take time, even more so in countries that have fragile institutions or are affected by conflict. So in parallel, we need to work on a second track, which is working on immediate operational continuity. So using alternative dissemination networks, simplifying workflows, trying to work on community level alerting, creating redundant communication channels, and so on. This is really to ensure that warnings are being delivered tomorrow, today, if possible, even while the system is being strengthened. And I wanted to illustrate this with an example that I've personally worked on, which is in Haiti, where the World Bank and other development partners have been committed to the long game for decades by supporting the national institutions of the country, despite political instability, security challenges, and so on. And that perseverance paid off in some cases, not always. I think it's safe to say that over the last 20 years, maybe the early warning system is a little bit stronger today. At least we have one concrete example where we have a more autonomous civil protection agency that was able to revitalize its volunteer network. This helps getting alerts faster and trigger action amongst local population when it matters most. At the same time, those communities couldn't wait a decade, because it literally took a decade for those reforms to mature. So in parallel, we supported more rapid, higher impact action by working with civil society. And one example was a nationwide preparedness campaign before the cyclone season, where through an NGO, we collaborated with local artists to reach awareness and readiness on cyclone preparedness. Maybe to conclude briefly, from this work, I think there are really three implications that emerge for weather services. The first one is to expand the focus beyond forecast production. And I think we've already heard from previous presentations how this is indeed very valid, not only in FCV countries. So forecast skill is necessary, but not sufficient on its own. The second one is that we need to integrate diverse operational and knowledge systems. Local intermediaries and community-led networks are often more reliable than formal channels, especially in countries that are affected by conflict. And I think we need to stop also seeing this as a weakness. This is actually an asset that should be intentionally designed into the system. And finally, when we're trying to design early warning systems for in a stressful environment, in a challenging environment, we need to design them for that specific reason. So they must be resilient to institutional fragmentation, to power outages, to territorial boundaries that may change, and mostly to misinformation. So this means building redundancy, distributed dissemination, and also working with trusted local interfaces. So I think those lessons are drawn from contexts that are affected by fragility, conflict, and violence, but they are globally relevant. And they really remind us that early warning systems are fundamentally social and institutional systems that host scientific information. I'll stop here. I think I'm really excited about this conference and really interesting to hear about all the presentations. Thank you so much, and really feel free to reach out. My email is on the slides if you're interested in this work and in collaborating further on finding solutions for such challenging environments. Thank you.
Thank you, Laura, for that very insightful talk. We have a question here in the chat. So I'll begin, of course, just jumping now. This question is from Philippe. Laura, you mentioned the need for long-term strengthening and immediate operational continuity. We see often short-term disruptions act as catalysts for long-term adaptability, but I'm worried it might create suboptimal costs for realized vulnerabilities and recognized weaknesses of the system. That is, companies providing solutions realize there's an immediate need for the fix, and the cost increases sharply. How do you convince stakeholders to act before that happens?
Yeah, that's a very good question. Thank you. I think we've also internally done a lot of thinking about this because our first goal is first and foremost to strengthen ideally state capacities. We still work with states. So when you start working with non-state actors, when you start empowering other actors in that value chain, there's a bit of a fear that, it may, first of all, as you said, you recognize the weakness of the system. It may undermine the trust even further. So I agree, there needs to be a lot of precautions and it needs to be very well managed. And it's not an easy answer or solution. However, I think we kind of have one premise or one principle, which is that there are so many things that can be done that we shouldn't wait, because again, working in development, the Haiti one is a very good example. You will wait 20 years for a minor improvement to happen, and in the meantime, you still have communities that are suffering every year or every 3 months, in that case, from recurring floods that are coming at the same time. You talking about contexts where it's going to be very difficult to invest in, drainage systems to just reduce that risk of happening that regularly, that often. However, early warning systems can at least prevent a little bit of deaths, of damages, and so on. And on the long term, what we see is that working in those two parallel tracks do end up strengthening the main system. I don't know if I responded entirely to your question. I'm happy to go more in depth, maybe follow up by email or another chat. But
that was great. Thank you so much. We're going to go ahead and move to our next speaker. Carolina Cerrudo is from the Meteorological Services of Argentina in Buenos Aires, and will be presenting advances in impact information analysis, early warning system thresholds, revision, and regional capacity building on impact-based forecasts. Carolina, you should be able to share your screen and take it away.
Thank you very much for the presentation. I will share my screen. Okay, let me see.
Yes.
Yes, it's okay, right? Right. Okay, thank you very much for the presentation. Good morning, good evening, and good afternoon. The impact-based forecasting and warning services project. Sorry, I have the bar. Thank you. That's okay. The impact-based forecasting and warning services project of our Med service aims to integrate impact information into weather forecasts, particularly for severe events with potential social impacts. So in this figure, you can see a summary of the different components that we are working on this initiative. We have established an interdisciplinary working group to achieve these objectives. I won't talk about all of this in this presentation, but I will focus on the analysis of impact information related to the design of impact tables and the revision of meteorological thresholds, as well as the development of a regional e-learning course in Spanish. So one of the results is that we have developed the South American meteorological hazards and their impacts database. Here you can see the web page where you can visualize the meteorological events recorded in this database. They are recorded in manual by people in a manual way. This database was co-developed between Buenos Aires University and the National Meteorological Service of Argentina. And it has also the collaboration of another institutions from other countries like Chile, Uruguay, Paraguay, and Brazil. On the right, you can see the categories in which the impact information is classified. You can see population and livelihoods, urban infrastructure and essential services, agricultural and livestock activity, transport infrastructure, trees, homes, and vehicles. So the development of these strategies of cataloging of impact data led us the improvement of the analysis of impacts. So this information was used to update the impact table for winds that we built at national level, and also for the analysis of the early warning service meteorological thresholds that I will show you in a minute. You can also access and download a quarterly newsletter from the web page. This product provides information on the impacts recorded quarterly into the SAMHI database in Argentina, Brazil, Chile, Paraguay, and Uruguay, as well as the sources of information used, the types of impacts generated by each meteorological hazard, the location of the main events, and the percentage of reports loaded containing information of impacts. For the development of impact tables, an analysis of the impact tables currently used by different and other meteorological services was made. On the left, here you can see some examples of the impact tables of reference. You can see the UK Met Office, United States of America, BOM Australia, and South Africa Met Service. And in the right, there is the impact table we have developed for wind at national level. It contains the description of impacts for different categories and levels for this one phenomena. In terms of the early warning service thresholds meteorological revision, and their relation to impacts. Here you can see the different steps of the process we have made. The main objective was the development and establishment of a working methodology to carry out this analysis. And here you can see our first step was the collection of information, then the evaluation and classification of this information. After that, the standardization of the format, because we collect information from different databases. And finally, the analysis of the information. The period analyzed was from December 2020 to August 2023. The phenomena analyzed rain, wind, and storm. The classification of impacts we used is the one I showed you before in the SAMHI database. And you can see in the map on the right, the study region. We have done this study for 6 pilot projects, small areas. You can see that our country is large, and we have done this analysis only this small area. So the principal challenge we have is to extend the analysis for both impact tables and thresholds revision. This is our principal challenge, and the problem is the lack of enough of impact information. But this process has been a great learning experience for us and led to the consolidation of work methodologies that can be replicated with further more information. Here I show you some results about impact analysis in 3 different regions with different characteristics. The figures represent the frequency of reports for different impact categories per month for rain. You can see in the upper left for Buenos Aires, the categories of transport and services stand out, followed by impact on the population and trees categories. In the upper right, in Córdoba, a marked annual cycle is observed with the highest recorded impacts in the transport category. And in Comodoro Rivadavia, in the south of our country, the transport and services categories stand out. Another thing to highlight is that the months with the highest number of variety of impacts are different depending on the region. May and August in Buenos Aires, in the east of the country. January and March in Córdoba. This is in the center of the country, and September in Comodoro in the south. So this slide shows some results in terms of the thresholds in these 3 same regions for rain. You can see box plots that summarizes the distribution of rain values for each impact category. And in color dot lines, you can see the values of early warning service actual thresholds. So you can see, for example, in the upper left for Buenos Aires, that impacts with values below the yellow alert thresholds are observed in almost all the categories. In the upper right for Córdoba, the values are largely distributed between the yellow and the orange alert thresholds. In Comodoro Rivadavia, for example, we can see that the percentile 75 is similar to the red alert threshold. Here I want to highlight 2 more things. It seems that in Córdoba and Buenos Aires, in the center of the country, an overestimation of the current thresholds is observed, but we have to take into account that these thresholds, the thresholds that we are using in the early warning service, they are in 24 hours, millimeters in 24 hours, and maybe these values have an impact, but in shorter periods, for example, in 1 hour. This is something that we are still studying, but it is a preliminary result. And in the 3 regions, the most frequent impact recorded is flooding of the road, street, or route from the transport category. So regarding capacity building, well, there is a gap in the availability of formal training in different languages. So since we started this project, we developed some formal courses. Here you can see 3 of them. First of all, in 2018, an in-person workshop for regional associations 3. Then we have developed an e-learning course in Moodle platform for our working group, capacity building for implementation of impact-based forecasting in Argentina. And last year, in the framework of the United Nations Early Warnings for All initiative, the regional training centers of Argentina and Peru, together with the Red Cross Climate Center, have co-developed an e-learning course in Spanish, which was promoted through the WMO Regional Office for the Americas. This course, called Strengthening Strategies, Collaborations for the Implementation of Impact-Based Forecasts, was given to the WMO Regional Associations 3 and 4. It was transversal, focused on the 4 pillars of the Early Warnings for All initiative, and had the main goal of facilitating collaboration opportunities for IBF implementation at regional level. Here you can see the high number of participants from different countries of the region that have participated, and also you can see a summary of the content of the modules with 3 main modules. The first one about fundamentals of IBF, the second one about partnerships and users, and the third one and last one information sources. I don't want to take more time being specific with this, but we can talk about this later. And as concluding remarks, I would like to highlight that the improvement of impact information collection methodology in terms of automatization and territorial extension will impact directly on the improvement of the impact tables and thresholds analysis. This improvement will also be made by the user's evaluation of the impact tables and thresholds that we haven't done yet, but we have an agenda to be done this year. Also, the expansion of case study areas and pilot projects. As you have seen, we have small areas and we need to expand the territory, the analysis in the territory, and more training that address the different aspects required for IBF implementation should be promoted. This was one of the results from our regional e-learning course, and the development of a cross-cutting approach with a regional perspective is really, really important. The course we have developed at regional level, it was very well received from the other countries. So I don't know if I'm good with the time, but thank you. Thank you for your attention. And if you have questions, I will be happy to answer them.
Thank you so much, Carolina. That was a very impressive efforts at a regional coordination there. We're just having some comments in the chat so far. So if anyone else has questions, please feel free to drop those in. But since we don't have any at this moment, let's go ahead and switch to our next speaker. Maria Inés Carvajal and Daniela de Amen are from the Universidad de Buenos Aires, also from Argentina. So please go ahead and you can give your talk on Beyond the Buzzword, what co-production really means for climate science users' knowledge and the limits of co-production.
Well, hi everyone. Thank you for the opportunity to present our work here. I will be sharing my screen. Let me see. Can you see my screen now? Yes. Okay, great. Well, I will be sharing this presentation with my colleague Daniela Damen from the University of Buenos Aires in Argentina. As social scientists interested in science-society interfaces, we are concerned with the central question: why, despite the exponential advances in recent years, has weather and climate information not been fully appropriated by different social actors? And related to this, how can we bridge the gap between the growing capabilities of climate sciences and the needs of decision makers? Over the past few years, we have worked both theoretically and practically, empirically, to explore these questions. The co-production approach has emerged and gained prominence in this field as a promising solution to these challenges. However, it has also been used in so many different ways that it risks becoming a buzzword. We are currently witnessing a collaborative turn at both national and international levels, bringing together the social, the natural, and environmental sciences in more interactive forms of knowledge production. There is a growing recognition of the complexity and uncertainty surrounding climate change impacts at the territorial level. This has highlighted the urgent need to improve climate and weather information, its accessibility, usability, and social appropriation in order to better inform decision-making, anticipation, and preparedness. So let me briefly distinguish two meanings of co-production that for us are the basic for starting these conversations. So the first meaning of co-production for us is analytical. It helps us to understand how science, society, power, and nature shape each other in unintended and unexpected ways. From this perspective, co-production is always happening, whether we like it or not. The second meaning is more pragmatical. It's practical. It suggests that when different social actors participate as equals in production of knowledge, the results are more legitimate, more relevant, and usable for decision making. This distinction is key for our argument because it allows us to see the co-production not only as something that already structures our world, but also as a deliberate strategy to improve climate adaptation and resilience. And it's not an unidirectional way, but is a relationship between the users of climate information and the scientific community. So if we take this distinction seriously, the next question is how to operationalize co-production in real-world context. For us, it is crucial to create problem-frame spaces where social and institutional actors can define priorities and agenda from the very beginning of the projects and programs. We know that knowledge co-production takes multiple forms and should be understood as a contextualized, inclusive, and deliberative approach. When knowledge is co-produced, we all know that it becomes more usable for all the actors involved. This, in turn, enhances its appropriation and practical application. With this conceptual framework in mind, I would like now to invite my colleague, Daniela, to walk us through a timeline of our practical involvement in user engagement initiatives in Argentina. The floor is yours.
Thank you very much. Hi, everyone. So now I would like to share with you our journey in user engagement and co-production. And our journey in user engagement and co-production has been extensive. It began in 2012 with climate services projects in the Inter-American Institute for Climate Research in articulation with the Regional Climate Center for the Southern South American region. Then in 2013, Ines conducted an ethnographic work during climate outlook meetings at the Met Service in Argentina. Then we have the Alertar project, that was a project that addressed severe weather warnings and focused on working with users in the emergency sector to understand decision-making processes and the use of weather and climate information. And a key milestone in the Met Service was the Meteorology and Society Division that this enabled the setting up of an interdisciplinary working group from the social sciences with an interinstitutional and intersectoral approach, which was really relevant to all the work carried out in the framework of the implementation of the new early warning service in the Med Service in 2020. And more recently, we have been working in CISA project at the Regional Climate Center and with international cooperation projects, which had objectives aligned in the sectoral analysis and focus on enhancing early warning services. Next slide, please. Here I want to share with you a very significant result that we would like to highlight in terms of the work process and also the coordination between Med Service and academia. Is this good practices for interacting with users of meteorological, climate, and environmental services guidelines, because it allows us to consolidate different work processes that have been under development, and it was a sustained effort over time. The work process over time was from 2020 to 2023, and then was finally published in 2024 in English and in Spanish. And it has also been an input for capacity building at the regional level in Regional Association 3 for South America. And this work involved first a team for project planning and the development of participatory activities, such as workshops and interview with different departments of the Med Service, and then for the development and initial diagnostic report. No? So it mainly addressed different methodological tools for approaching and working with users based on their specific needs, and it also proposes strategies for the production of information and systematization of relevant data that serve an input for the definition of work processes and coordination of interviews, surveys, and workshops. Next slide, please. So here we have identified several critical points in our experience in user engagement in Argentina and also at regional level. No, there are multiple definition of co-production is often applied to different contexts, which in many circumstances limits reflection on processes and the promotion of improvements. There is still a low participation of social scientists within national meteorological and hydrological services. And as a result, many of these practices are spasmodic, are mainly carried out by meteorologists or hydrologists. And this is a point that we were able to identify in our work experience at the regional level in South America. To move beyond the buzzword, we must continue building capacity and ensure that co-production remains a rigorous subject of conceptual analysis and methodological innovation. Next slide. We're here to conclude some challenges in user engagement process. In terms of challenges and critical points that must be considered in these issues, it is essential to sustain these processes over time, supported by the institutional efforts that establish these approaches as necessary. There is still much to be done in terms of monitoring and evaluation of these processes and dynamics, considering the positive impacts on weather and climate services when work mechanisms are established focusing on co-production and user engagement strategies. And then we face significant challenges in addressing both the first mile and the last mile of communication and engagement. We consider this to be a very interesting and fruitful discussion, which was also raised during the first Weather and Society conference. And the importance of providing weather and climate warning from the very beginning. So users should be part of the whole process, developing products and services. And it is necessary to involve users, stakeholders, partners, and there is also a discussion about this user category. ensuring that their needs are met with weather and climate warnings and information. So thank you very much for your attention, and we are happy to answer any question you may have.
Thank you so much for that talk. As we wait to see if some questions will come in the chat, I'll go ahead and throw one out that maybe is a bit broad, but these challenges with incorporating users are, I think, it's a recurring difficulty. So what have you seen, especially related to sustainability, sustaining engagement over time, to be some of your best practices that you think would be transferable in operational contexts in other places? How do you keep up user engagement over time?
Well, that's a very good question. It's the key question here, how to sustain interactions over time. I think that we have two main levels here. The personal level is how we as experts, scientists, professionals can engage in this journey of meeting with users and sustain interactions over time, beyond the work that we do in our daily basis. Particularly when we have funding, it is easier. But then when we do not have any support, then it's more challenging than expected. But then we have the institutional challenge because, for example, in the National Weather Service of Argentina, now we are suffering a lot of economic, financial crisis. So it is difficult to sustain that important spaces if it is not a priority for institutions, for example. But this is very challenging in a way, in a very broad way. But I think that we need to strengthen our capabilities to deal with these challenges. I think that a best practice is to try to build trust with users, so we can know what are the expectations, the needs, and we can show also the limits of science. How can we say the probabilities? How can we express better the knowledge that we have to better inform decision making in a daily basis for different sectors in different territories? Daniela, would you like to add something?
Yes, I think as we mentioned now in our presentation, I believe this is what we wanted to emphasize, that these are long processes, that require trust, as mentioned Ines before, and also institutional arrangement are really important to sustain this, and the role of social scientists trained in these issues and to promote this research organization. I think there are key points, and of course it's really difficult and it's crucial to think about that, but it's essential to involve users in these processes. Also, this discussion of where involve user, I think that should be from the very, very beginning, and always keep in mind the reflection on the process of knowledge production. I think that it's really important, and also is thing that should be taken into account from the med services, because really changes the way that services and products are delivered.
Well, thank you so much for this very insightful talk, and thank you to all of the speakers. Dawn, did you want to jump in?
Yeah, sorry, we have a slight change in plan that Katie did not know about. We have a couple of announcements that we wanted to catch people really quickly before we move into the scheduled break. So Isha's going to pull up some slides. So these are a couple of things. One is this call for papers that you might have seen. So get your phones out and take a scan of the QR code if you want. but this is something that will be coming out later, or we're accepting papers through much of this year. So please take a look at that at the NPJ Natural Hazards for this new collection, very relevant for what we're doing. Slide 2 is this survey that we would also love for people that are participating in this conference to take advantage of. We would love to get your input on this data. Looking, as it says, it's for social science capacity and experiences. Some of you may have seen this already. It's also gone out in some emails, but we're taking this opportunity to bring it to your attention here also. We'd love to get your feedback. And there is one more slide, I believe. And then we're just gonna get all kinds of QR codes going here. A survey for feedback on the conference itself. We'd love to do this. This has been the third time that we've done this. We like to think it's been getting better each and every time, but we certainly know there's room for improvement, and we would love to get your feedback on how we can do that. Okay, Katie, back to you. Thank you.
Certainly. So now we have time for a short break. We've got around 12, 13 minutes. So we'll begin our next block moderated by Monika Giri at the top of the hour. So that would be 22 UTC time. With that, we'll take this break and we'll see you back shortly. Thank you for being here.
All right, welcome back, everyone. Now we'll be going through the last set of presentations for the session today. We have 4 very interesting talks lined up. And as a reminder, each speaker will have 12 to 13 minutes for the presentation, and we can have a few minutes for questions. All of you, please feel free to drop your questions for the speakers in the chat, and kindly keep yourself muted and help us run through smoothly. Now I'd like to welcome our first speakers, Luis Baldeón and Daphne Elizabeth Herinazians from Peru, who will be talking about ancestral signals for short and long-term weather forecasting. So if you could start sharing your screen, the floor is yours, Daphne and Luis.
Okay, thank you. Do you see my screen?
Yes.
Okay.
But it's not in the oh, yes, it's perfect now, yeah.
Yeah, okay. Well, good afternoon, I guess. My name is Luz Angelica Baldeón Ramos, and I am a meteorological engineering and climate risk management student from the National Agrarian University, La Molina in Peru. Today, I will present our work titled Systematization and Categorization of Ancestral Signals for Short and Long-Term Weather Forecasting in Peru. Well, this study is part of a broader initiative called Raíces Climáticas, means climate roots, which aims to transfer ancestral environmental knowledge into structured and analyzable climate information systems. So, okay. Well, to begin, it's important to clarify what we mean by ancestral signals. We are not just referring to symbolic beliefs or folklore. We are referring to empirical observation systems. Well, across Andean communities, environmental forecasting has historically relied on careful observation of animals, plants, stars, and atmospheric conditions. For example, change in animal behavior, plant phenology, or the visibility of certain constellations are interpreted as indicators of upcoming rainfall conditions or drought. Well, these interpretations are based on repeated environmental observation across generations. So in practice, they function as localized forecasting systems built on pattern recognition. About climate context in Peru, well, this work takes place within a highly complex climatic context. Peru contains 38 climate types according to the turn weight classification used by Tsunami. The result is strong climatic heterogeneity, high agricultural dependence, and significant exposure to hydrometeorological risk. In such contexts, localized forecasting becomes essential for adaptation and risk management. About the structural gap, ancestral forecasting knowledge already exists. It is documented and actively used in rural communities. However, it remains fragmented. The information is dispersed across reports or institutional documents. It's not standardized, not comparable, and therefore not integrable into formal climate services. So the challenge is not recognition, the challenge is structure. Without systemization, this knowledge cannot meaningfully contribute to early warming systems or climate service frameworks. Fragmentation prevents usability. So the purpose. The purpose of this research is structural. We aim to move from dispersed observations to structured climate information. Within Raíces Climáticas, this study functions as a methodological bridge. It creates the data architecture necessary to translate qualitative environmental knowledge into organized, analyzable datasets. Because without systematization, integration is simply not possible. About the methodology. To do this, we conducted a structured bibliographic review. We initially identified 40 sources related to ancestral forecasting knowledge. However, only 7 met strict criteria. They had to explicitly describe a forecasting signal and its associated interpretation. From this source, we extract more than 500 individual signals. Each signal was then coded into a structured database. The database includes the type of signal, the observed characteristic, the forecast interpretation, the predicted phenomenon, the intensity or attribute, the temporal scale, and the territorial context. An important methodological aspect is that a single observed characteristic may lead to multiple forecast interpretations. Like, for example, the brightness and visibility of the playeras can indicate different rainfall scenarios depending on how it's described. Also, each interpretation is coded separately, allowing one signal to generate multiple structured forecasting combinations. Well, this is our website prototype. As a part of Raíces Climáticas, we also develop a website prototype. This platform serves as a structured consultation interface. It allows signals to be organized by region, type, and predicted phenomenon. Well, it allows signals to be organized by region, type, and predicted phenomenon. More important, it creates visibility and accessibility in a format that could eventually connect with local climate services. Well, about the results, in this initial phase, the signals collected corresponding primarily to the Andean region of Peru, Puno, Huancavelica, and Cusco. Future phases aim to expand geographically and incorporate more direct collaboration with communities. As I said, in total, more than 500 signals were systematized. This volume demonstrates that ancestral forecasting knowledge is not anecdotal or isolated. It is extensive and structurally consistent. The most common is the type of biological. About forecasting scale, most of the collected signals are associated with medium-term forecasting scales. Approximately 48.8% correspond to forecasts made weeks to months in advance. This suggests that ancestral observational systems are primarily oriented towards seasonal anticipation rather than short-term daily prediction. Well, in practice, this means these signals function as tools for planning agricultural activities across the seasonal cycle. This becomes particularly relevant in regions where institutional seasonal forecasts may not be locally accessible or territorially specific. Well, what kind of signs do they use to predict? Well, this picture is in Spanish, but in terms of observed indicator, nube means cloud. Cloud characteristics appear as one of the most frequently used environmental signals. Change in cloud type, density, or movement are commonly interpreted as indicator of future prediction conditions. This reflects a forecasting logic grounded in atmospheric observation rather than abstract indicators. So community are not only observing biological behavior, but also real-time atmospheric dynamics such as cloud formation to anticipate rainfall variability. When we analyze the predicted phenomena associated with these signals, rainfall clearly dominate the dataset, rain or cloud. In generally, more than half of all collected signals are related to hydrological variability. This distribution indicates that forecasting practices are strongly oriented toward anticipate precipitation patterns and weather availability. This is consistent with agriculture dependence of Andean territories, Andean communities. What are their forecast interpretations like? Well, this figure shows how environmental signals are interpreted in terms of forecasting intensity and predicting phenomena. Like each code Entry represents a combination such as present plus rain, here. Present plus rain, increase plus rain, or late onset plus rain. We observe that rain-related forecast combination dominate both wet and drought seasonal interpretations. For example, within wet season forecast, presence plus rain appears 161 times, while increase plus rain appears 51 times. So in drought-related interpretations, combinations such as decrease plus rain or absence plus rain are also frequently identified. In total, approximately 445 code signals related directly to rain variability. So this indicates that ancestral forecasting systems are primarily oriented toward anticipate water availability, including rainfall timing, intensity, and deficit conditions. So rather than prediction climate in general terms, these systems function as anticipatory mechanisms for hydrological risk management. What does a community gain? Well, at this stage, the project does not aim to directly integrate ancestral knowledge into formal weather forecasting systems, right? What we are doing is creating a structured visibility window. By categorizing and systematizing these signals, we are transforming dispersed knowledge into organized information. This allows ancestral forecasting practices to be documented, preserved, and also analyzed without losing their original context. Well, for communities, this means recognition. It means their knowledge is not treated as anecdotal, but as a structured environmental observation. And obviously, in the future, this structured format could facilitate dialogue with local weather services.
I'm sorry, Luis. I'm having to cut you off in the middle. We are a little over time, and we might have to move to our next presenter to respect their time and also keep everything according to schedule. Yeah, if there are any questions in the chat, I hope you can answer the questions there. Thanks again. So I would like to invite our second speaker, Sarah Harrison from Earth Sciences New Zealand, who will be talking about urban bias in impact-based forecasts. You should be able to share your screen, Sarah. Over to you.
Okay, thank you.
Thanks, Luz, and thanks, Monica. I'll just, okay. Sorry, I'm not used to Zoom, so just figuring out the mechanics. Okay. To confirm if you're seeing the correct screen. Okay.
Yes. Yeah.
Thanks. Yeah, kia ora, hello, good afternoon, good evening, good morning, everyone. Thank you all for hanging in here if it's a late night for you. So I'm Sarah Harrison. I'm a hazard and risk social scientist at Earth Sciences New Zealand. Formerly, we were GNS Science, so that might ring some bells, but we've since gone through a merge, and now our new name is Earth Sciences New Zealand. So today I'm going to talk to you about a concept or a theme that's been kind of emerging through some various projects and works that I've been involved in, most recently in the work that Joanne Robbins recently presented on with Sally Potter, but I'll also pull on other work as well to talk about this topic of urban bias in impact-based forecasts. So to start with, I would like you to just kind of challenge the assumptions that we have in data-driven approaches and think about when we're designing impact-based forecasts and warning systems, whose safety are these forecasts actually designed to protect, and whose is quietly being deprioritized. So here we have some examples of severe weather events in New Zealand over the last few years. And they produced a lot of significant impacts and a lot of cascading hazards such as landslides, floods, mud flows, etc., and a wide range of communities, including urban and rural communities, were significantly impacted during these events. So in terms of impact-based forecasting, I did some previous research on kind of what data we need for impact-based forecasts, and in line with all the literature that's already out there, we found that we need a few different data sets, and this was already pretty much covered in Joe Robbins's presentation. But the idea of impact-based forecasts and warnings is to make these warnings more relevant to our target audiences, and this requires knowing who those audiences are and what they need. And when we're developing a system, we need a few different data sets, like I mentioned. So following along the warning value chain at the bottom, obviously we need the hazard data, and that could be the meteorological observations, the models from that, as well as rainfall forecasts and landslide forecasts, for example. And then we need to combine that through either a model-based approach or a subjective discussion-oriented approach, like the spectrum of approaches that Jo had in her slides. But we need to combine that with either knowledge or data around impacts, exposure, and vulnerability. And from there, we can produce some kind of decision or advice for actions, and we can use other social data, for example, observations on social media or survey data, to try and design the advice more accurately. So the questions that we've been trying to address in this previous work or ongoing work is kind of, what does including these data-driven approaches, or what does it look like when these approaches are more data-driven and we include exposure and vulnerability data into the process? Oh yeah, also there's cascading uncertainty along the chain, forgot about that. So as we add more data sets and more modeling, that kind of exacerbates the already existing uncertainty. So back to the question of what happens when we integrate these different data sets. I would like to introduce the concept of urban bias. It's not a new concept. It's been applied in economic and political analysis and discourse. It was coined by Lipton in 1977. So the original definition of urban bias is the tendency of public authorities and private persons to allocate and their disposition to justify for large urban areas proportions of developmental or welfare-generating resources in excess of any reasonable norm of either efficiency or well-being. And just looking at this very oddly shaped map on the right, you can see that we have one significantly larger urban center just based on population in New Zealand. And then we have a few other urban centers like Wellington and Christchurch. And then all the other parts of New Zealand are quite sparsely populated. So we do have a really significant kind of urban-rural divide spatially and demographically. In New Zealand, 1.5% of the land cover is classified as urban, and that's home to almost about 84.3% of the population. And the remaining 98.5% of land cover is classified rural, which is home to 15.7% of the population. So that's just to give you an idea of kind of our spread here in New Zealand. And when we look at, so urban and rural areas in New Zealand experience severe weather differently, like I was already kind of alluding to earlier. And when we look at what happened in early 2023, where we had severe flooding and Cyclone Gabrielle come and impact much of the North Island of New Zealand, comparing between urban and rural settings, we can see that these two different areas experienced the events very differently. So in urban areas like Auckland, the hazard unfolded really fast, and flash flooding quickly overwhelmed stormwater systems, damaged rental properties, and displaced low-income households. Disabled residents were particularly affected when power and internet failed, and emergency services were inundated as well. Auckland Council saw about more than 800 callouts in a single day. In contrast, in rural regions, such as Wairoa and Tairāwhiti in the east, faced prolonged isolation following the event. They experienced washout bridges and roads, which left communities cut off for weeks, with major economic losses across farmland and large areas buried in silt and forestry debris. Rural marae, which are the kind of community gatherings for Māori, the indigenous population here in New Zealand, and the rural communities became their own first responders and supported people and animals when official help couldn't reach them. In terms of warnings, they also played out differently. And this is all a summary from several post-event reviews that were completed following this event. So what I'm telling you now is a summary of all of those investigations. But in terms of warnings, in the cities, short lead time thunderstorm warnings relied heavily on digital alerts, but these actually failed to reach elderly, disabled, or non-English speaking residents. Meanwhile, in rural areas, telecommunications networks collapsed entirely, and that left radios and local knowledge to be relied on more so than digital tools. So these post-event reports suggest that pre-positioning satellite communication in places known to be isolated could be a solution. So based on all of this context, the question that I want to try and start to tackle through this conversation today is, how might urban bias come through by including exposure and vulnerability in impact-based forecasts and warnings? And this is also touched on in a publication by Potter et al., which you can access through the QR code down there. So in the first example I want to talk about, Sally Potter is going to talk about this project. This is the other half of the project that Joe Robbins already talked about. So I'm not going to go in depth into the methods or the results, just more about one interesting finding that we've seen, at least in the New Zealand case study. So when we compare hazard people, the hazard people exposure approach, so this is the assigning warnings based on human exposure. When we compare that to assigning warnings based on building exposure, so this is basically population counts per area versus building counts per area, we can see a flip where red warnings in the people-centered approach, the people exposure approach, are really concentrated in the urban center, which is Auckland. But if we flip it to buildings, building exposure, the red warnings are actually more outside in the more kind of rural area of the Auckland region. And if you compare that to the official classification of urban-rural areas in New Zealand, you can see pink is urban areas, that's the Auckland CBD essentially, Central Business District, and then rural is all the areas outside of Auckland. Essentially. And so you can see that there is some interesting correlations there when we base warnings on people exposure versus building exposure. So we can see that more people are centered in the Auckland than they are outside of Auckland, but apparently more buildings are outside of Auckland than they are inside of Auckland. So tune in to Sally's talk later on in this session for more on this project. In another example, in another project that we're doing, we're evaluating some prototype rainfall-induced landslide forecasts that GNS Science at the time, now Earth Sciences New Zealand, issued in response to the Cyclone Gabrielle risk. So first we have this rainfall-induced landslide probability forecast, which shows you which parts of the country have the highest probability of a landslide occurring per grid cell. And then this was essentially overlaid with some property data. So this is properties per ward. A ward is the area defined. And you can see that Auckland, again, comes through really strongly as having the most properties per ward that will be affected by a landslide. And when we were interviewing the users of these forecasts to see how they received the forecast, whether they used them in the event, what kind of challenges or limitations they experienced with these forecasts, several interviewees actually questioned what was driving this this result with Auckland coming out like fully dark. Is it the fact that Auckland actually was more significantly hit by the event, or is it just that Auckland has more buildings, more people, and therefore they're always going to come out more heavily on these maps? Again, this is kind of a question around that urban bias. Is this what we're seeing here? If we compare it to the New Zealand Social Economic Deprivation Index, the light pink color shows the least deprived, and the dark red shows most deprived. So this layer wasn't actually included in the landslide forecast analysis. This is just comparing, so you can see the areas. Let me see if I can try and use a laser. Yes. So up here we have quite a lot of high probability of landslide activity. But here it comes out a little bit darker. And is that because there's just less buildings up there? It could be. But here, if we look at the deprivation index, this area is actually more deprived than the Auckland CBD is. And likewise down here on the east, southeast part of the map, this came out quite high probability. No properties apparently affected, but it does have high deprivation index. So just to unpack the deprivation index a little bit more, what's involved with developing these indicators, developing the index. I wasn't involved in it. This is someone else's work. But it's basically people with no home or internet access, receiving means-tested benefits, people who live in equalized households with income below a certain threshold, people who are unemployed, people who are not living in their own home, so renters, people aged less than 75 years living in a sole parent family, people living in households below a bedroom occupancy threshold, and people living in dwellings that have a significant amount of mold in the rooms. So that's what's used to develop this deprivation index. And a question that I had for myself when I was looking at this was, well, what about reliable access to cellular networks? So we have an indicator here about internet access, but what about cell phone networks as well? Because in my third example, are you seeing a blue circle? Sorry. Hopefully you're not. Anyways, so in my third example, when we're looking at public alerting mechanisms and the different channels that we use to reach people, the aim is to reach at least 70% of the population. In New Zealand, emergency mobile alerts, so those are alerts that are delivered through your cell phone, are now considered the reliable backbone for reaching most of the population rapidly. But when we think about cell phone network coverage, it's pretty spotty in New Zealand. And again, pointing out those areas with high deprivation, they have quite spotty coverage due to terrain, but also due to lack of kind of infrastructure development in those areas. And we compare it to our population density, you can see that these areas are not unpopulated. They have people living there. So there are essentially people living in areas with unreliable internet coverage. And there's a report
stepping in again, Sarah. I'm so sorry.
Okay.
Yeah, so I cannot see any questions in the chat yet, but if there are any, I hope you can answer them there.
I'll just share this last slide if anybody wants to.
We have to move on to the next presentation. Our third speaker is Jinjuan Liu from Adelaide University, Australia. who will be presenting the global assessment of heat health warning systems. If you could start your screen, Xinjuan, the floor is yours.
Yeah, yes. I'm not familiar with Zoom. Yeah, I'll try to do it quickly. Share screen. Can you see my share screen?
Yes.
Okay. Yeah. Okay. Cool. Good morning, good afternoon, and good evening. My name is Jasmine from the Adelaide University, Australia, and today I'm going to present you our research on the assessment of heat house warning system, focus on how they operate, whether they are effective or how they can be improved. Okay. So first, a bit of background, why we need a heat house warning system. Extreme heat is no longer a rare event. It's becoming defining feature of our climate. I gave an example here. In June 2024 alone, nearly 5 billion people were exposed to climate change-driven extreme heat over just 9 days. So heat, unlike many other natural hazards, it's considered as a silent hazard and is now the most widespread and fast-growing natural hazard globally. It also contributes to substantial excess deaths, healthcare costs, and associated economic disruption. What is heat house warning system? The heat house warning system is a coordinated system linked meteorological data, public health, and emergency response. It defined as a mechanism aimed at minimizing negative health impact of heat by alerting authority and warning the public. But it's important to know that it operates in an assumption of benefits to public health by avoiding heat-related mortality and morbidity. The heat house warning system now is one of the most scalable public health adaptation tool to extreme heat. However, globally, we still don't have a clear picture of how these systems operate, like the landscape or whether they work or not, or for whom is effective in what context. So here are the three core questions we trying to address in our research. First, the operational landscape of heat house warning system across the globe. And second, we evaluate the effectiveness of the system in reducing heat-related mortality, morbidity, or whether it increased protective behavior. And third, the pathway for improvement. How can the heat house warning system be strengthened moving forward? Our systematic review has been registered in Prospero, and we conduct search on 3 databases for literature published up to July 2025, which we think we will conduct and update research maybe this month before we finalize the manuscript. And the search term combine heat exposure concepts such as heat wave, extreme heat, and paired with warning and preparedness terminology, including heat alert, early warning system, or disaster preparedness. So that to capture both operational and outcome-focused evaluation across diverse contexts. This slide shows the PICO framework for eligible assessment. So for the population, we include all population group exposed to heat, and the intervention was the implementation of heat house warning system with or without formal heat action plans. And the comparator include non-alert day or pre-implementation period or the usual practice.
And outcome range from mortality, morbidity to behavioral response and system performance metric. And for the study design, we include quantitative, qualitative, and mixed method study. And this slide shows the Prisma flowchart of the study selection process. So in total, we identified nearly 3,000 records. And after screening and eligibility assessment, 95 studies were included in the review at this stage. And throughout the process, we applying a double-blind approach, which means at least 2 independent researchers would conduct the screening process. And the data extraction will conduct independently using a standardized template within Covidence. And this map shows the geographic distribution of the heatwave warning system study included in our review, and the level at which the intervention were implemented. And each pin represents a study location. And the pink color here indicate the scale of implementation from community-based and city or local-based intervention or national or multinational initiative. And in the background, the shade continent summarize the number of heatwave warning system study by continent, with darker shading indicate a higher concentration of study. And overall, we can see that the study are mostly clustered in Europe or North America and part of Asia, with comparatively fewer studies identified in Africa or South America, And we also notice that in Europe, it's predominantly characterized by national or multinational heatwave warning system initiative. However, the study in North America and Asia are frequently implemented at the city or community level. And this slide shows how the heatwave warning system evolved over time. The top figure shows the scale of implementation over time, and that we can see in the early period, roughly 1996 to 2010, the implementation was predominantly city level or subnational level. However, after 2015, we can see an increase in national or multinational heatwave warning system initiative. And the figure in the bottom shows the evidence was predominantly come from high-income country, no surprise. And only in the past 5 years, we observe a gradual increase in upper and lower middle income contexts. And here we summarize the results of methodological pattern by study design and outcome focused from the included evidence. And on the left-hand side, we see the distribution of study design. Nearly 40% of the study now mainly focus on the system performance evaluation, including like the trigger accuracy, the threshold sensitivity, and timeliness. And mixed method study accounts for about 1/4, while the qualitative or observational time series study each contribute around 13%, with only 11% using quasi-experimental design and 2% involve randomized or natural experiment, meaning the rigorous causal evidence remain limited in the literature in the field. And on the right-hand side, we see what the outcome being evaluated. The largest share focus still on system performance metric, like accuracy, the lead time, and following with behavioral outcome by 18%, and mortality or equity of 60%. And together, these patterns suggest that the literature is heavily weighted towards like how the system function technically, rather than whether they consistently reduce health impact at the population level. And in this slide, we summarize the evidence on the effectiveness of heat health warning system in reducing heat-related mortality. And on the right-hand side, we present relative effect expressed as risk ratio for all-cause mortality during heat event with active warning system. And we pulled a relative effect from comparative study using random effect meta-analysis. The overall association is very close to insignificant, with the pool risk ratio of 0.99. And we also noticed moderate heterogeneity across the study. However, several city-level or quasi-experimental evaluation report protected effect following the introduction of heat health warning system. And like the larger national analysis tend to show little or no average impact, in particular those from US. And on the left-hand side, we present absolute effect report either as deaths prevented per day or as reduction per 1 million person per day, like the life saved after the system alert. And across the study, the point estimate suggests a reduction in mortality following the heat wave warning system implementation, with a clearer benefit often observed for like the high risk group, elderly population, or the cause-specific, heat-specific cause. And taken these together, this finding reinforce our assumption the effectiveness of heat wave warning system is really context dependent rather than uniformly protective. And next, we turning to the morbidity outcome, which include hospital admission, emergency department visit, and ambulance call out. And this graph mainly shows the evidence from the elderly population. And the pool relative estimate show reduction in some city level. The pattern is similar to what we found for mortality. And it showed reduction in some city level analysis, particularly for heat-related or cause-specific outcome. And again, national level study often report non-finding or insignificant effect. And in some cases, like the study from US, they also show even increase in hospital admission following the alert. This may reflect increased health-seeking behavior during a warning period. Maybe the alert improve awareness or earlier presentation to the hospital or clinic. And next, we look at heat-related prevention behavior. And across the study, heat warning are associated with increased use of like the cooling strategy, including fans, AC, or water intake, and people's behavior like reduced outdoor activity. And unlike mortality or morbidity, the finding from protected behavior appear more consistently responsive to the warning alert. And next we try to dig deeper. So why are the mortality and morbidity results mixed? And we try to answer this question by looking at the variability of system performance. From the evidence we collected, we synthesized in 3 main themes, which have touched by previous presenter also. First, the trigger design method. The health-based threshold can work well, but different heat metric flag different dangerous day. And And somehow, a couple studies indicate more complex indicators are not always better. So it really context specific. And second, alert doesn't always match the real health burden, similar to what presented by Sarah. The map and many illness and deaths happen on non-warning days. And the warning frequency can also reflect, the climate, like the exposure, rather than the health risk. And the alert area may not line up with where the impact are highest. And third, the system work better when they combine forecast with lead time and real-time health surveillance, so they can act earlier and adjust based on what happened. And next, we after looking at the effectiveness and the variability of system performance, we put together the evidence from qualitative and the mixed method survey. And the evidence tell us like the warning don't automatically translate into protection. And the implementation and equity also determine whether an alert can protect people. And I also want to mention.
Would you like to wrap up?
Yeah. The last slide. The many systems like currently assume a simple chain. We assume as long as we issue an alert, people would receive it and people would understand it and action taken, and everyone be protected. But in reality, the evidence shows that the system would often like break down, which we summarize in 4 aspects. The first, the awareness is common, but action is uneven, because the information alone is not enough. And the second aspect is many barriers are structural. It will constrain people's ability to act. And the third point is like the equity gaps are consistent and actually predictable. For example, the language and cultural tailored message or action are needed. And the vulnerable population are often at the least reached. And finally, the heatwave warning system tend to work better when there's a strong coordination, a clear road of department, and trigger link action more clearly across agents. And here we summarize the 3 pathways that can improve heatwave warning system, how to improve detection, improve like translation, that's communication, and ultimately improve real world impact. And thank you for your time and attention. And please scan the QR code if you have like any feedback, like for the presentation, and we're happy to touch base and work collaboratively. And thank you very much for your time.
Thank you. Thank you so much, Joan. Now I'd like to call our 4th and our last speaker for today's session, Sally Potter from Canary Innovation Limited, New Zealand, talking about impact-based warnings using risk modeling.
Thank you very much, and thanks for sticking with me here, everybody. I really appreciate that. So I'm from Canary Innovation in New Zealand, and this is a consultancy and social science research outfit that can help to improve forecasts and warnings. I just want to confirm, can you see that okay, Monika?
Yes. Yeah.
So as Joanne Robbins already presented on before, we've been looking to explore what the implications are when you incorporate exposure and vulnerability data into your impact-based warnings. She presented on the UK results, and I'm going to be presenting now on the New Zealand results. I'd like to acknowledge my co-authors there. And I've got the QR code for our paper up in the top right. That was when we explored what the benefits and challenges are of impact-based warnings. One of the key challenges we identified was having this robust data to base your impact-based warnings and your thresholds on, because impact-based warnings need to have that hazard and likelihood information, as well as the exposure and vulnerability data, especially when you're having a more quantitative risk modeling type approach. So this study was really to explore what are the effects if we actually do incorporate those kind of data into those decision-making processes. How does that affect the number of people that would get warned? So for the New Zealand case study, we were looking at Auckland City, as Sarah mentioned already, up there in the North Island of New Zealand. We used a cyclone hazard scenario, which I'll talk about next. We then put on the building exposure and vulnerability data to determine what are the impacts going to be. And then we produced sort of synthetic or hypothetical warnings using those scenarios to see how many people would get warned. So in case you're interested in the data that we used, here it is. We've got the hazard scenario, which I'll talk more on next. We used kind of more the government type data for building inventory data sets, the population. We use the statistical areas or SA2 levels, which are just kind of little bound area units depending on how many people live in that area, and that's why they're different sizes. So the rural areas have bigger areas incorporated in them, and then the urban areas have tiny little ones. We've got the vulnerability, so that uses building asset data. So in particular, what are they made out of? How are they constructed? And here's that wind hazard information. So previously, before this study, some researchers got Cyclone Cook, which came over New Zealand a number of years ago, but it just missed Auckland. It was out to sea a little bit. So what they did is they picked up New Zealand and they moved it underneath the path of this cyclone and then remodeled what that wind would look like. So that's the data set we use. So in some ways it's a bit hypothetical, but it was a real event. We just wanted to hit Auckland for this exercise. So this resulted in wind gust speeds of over 200 kilometers per hour on that area, and I did convert that. That's 124 miles per hour. And then most of the area had 180 kilometers per hour, which is 112 miles per hour across it. So you can see it's a lot of strong winds. There's going to be a lot of warnings going on here. So for that first experiment, we wanted to know if the thresholds are just based on the level of hazard or wind speed, what would the warnings look like? And this is it. We've got mostly red warnings going over the study area around Auckland there. The thresholds that we used for these warnings were just what Met Service told us they would typically use. And again, I've got the conversions there into kilometers per hour, miles per hour, but basically almost all of this area is red using this, this methodology. The second experiment used exposure. So first of all, we've got the exposure of people, and then we had the exposure of buildings to that wind. And they've got the thresholds there as well, use the Jenks natural breaks to get those. And what we did is use the same hazard thresholds on that matrix there as in experiment 1. And then we put the exposure either of people or buildings on the other axes of that risk matrix to determine what level of warning each SA2 area would get. This is the results for the people being exposed. So we've got that population distribution map on the left. You can clearly see Auckland City there with higher population areas. And then we put that through that matrix, and you can see on the right that a lot of that high population area is getting the red warnings. And so that means 24% of our population in this study domain would have got a red warning using this, a lot smaller than when we had just used the hazard-based thresholds. Now, if we look at where buildings were and how they were exposed, you can see this is actually quite different. We thought this was a bit surprising at the start. We thought there were a lot of buildings in the urban area of Auckland, and therefore it would still get lots of red warnings in there. But what we figured out was because we're using these SA2 areas, they're quite small, and in the middle of the city, you might get like one apartment building with lots of people in it. And so there are actually less buildings there in those little per area than in those more rural areas, which are really large and have, perhaps a lot of farm buildings and just towns and lots of separate houses in New Zealand. So you can see there that only 3% of the population actually got a red warning using this building exposure method. So hugely different to the hazard approach. And then with experiment 3, we have, this is a very complicated slide, but it's really there for people who are interested in these fragility function type of things. The take-home message here is we calculated using the risk software what the potential damage would be to every one of the buildings in that study domain. So we used a vulnerability function there, and basically it's saying if it's a timber building, it's more likely to get damaged by high wind than a masonry building. We've got mainly timber buildings in New Zealand. Any of those areas that had any buildings that were severe or collapse from that wind, it would get a red warning. It'd be orange if there was any moderate damage, and then so on, and yellow and no warning. Now, there is a bit of a complication here as we don't have that many deaths in New Zealand from wind causing damage to buildings. So we had to rely on overseas data, often from tornadoes. So there are uncertainties in this, and this will come out a bit later. Here are the results. So you can see here that we had 300 buildings modeled to have severe damage. A lot of buildings would get that minor damage. That's that graph on the right side there. But largely it's the areas that were really exposed to the strongest winds coming from that cyclone and that had a lot of building damage there. Those are the red areas. And so less than 1% of the population would get a red warning using this approach. Here is where we can compare those 4 different approaches. So you can see the hazard column has a lot of red warnings, going through to the risk one, which has mostly yellow warnings. So the key implication here is that if you are starting to move towards impact-based warnings, what are you using? What data are you using? Are you using exposure? And if you are, exposure of what? Is it of buildings or is it of people? Are you incorporating that vulnerability data? Now, we've only included vulnerability of buildings in this assessment because that's what our fragility function could do. We didn't have one on wind straight to people and life safety. So we couldn't do that extra step, which would be good to do in future. But it really reflects on that question Joanne was talking about, is what is the purpose of that warning? Who is it for? Because it's got huge implications on who gets warned, depending on how you want to incorporate this kind of data. Sarah talked about the urban-rural bias, and this is where those results come in. You can see here that the urban areas had higher warning levels when you looked at population exposure, but when you looked at building exposure, the rural areas got the higher levels of warning. So that was an interesting find, and really just highlights you've got to critically analyze what is being exposed, what's your data relating to. And in terms of uncertainties, yes, we've got uncertainties as per always on our hazard information, our weather forecasts and so on. But if you're incorporating this other aspects of risk, you've got that missing asset data. You might have seen in the graph, there was a big column of missing data to do with the buildings. So that's a huge uncertainty. But then even the building asset information that you do know will have uncertainties as well. They could be quite inaccurate. And then if you start taking into account exposure of people as well, and then you think about how people move daytime versus nighttime, you've got those dynamic changes, which really brings in uncertainties as well. And then in terms of the vulnerability functions, as I said, we're using overseas and based on not many deaths at all, so there are big uncertainties in that vulnerability function. And the uncertainties were so huge on the impacts on people, the vulnerability of people, that we just couldn't even use it at all. So how you try and accumulate those uncertainties, bring them all together into a quantitative impact-based warning approach. The point is, at what point do these uncertainties get so huge that it's not useful anymore, and that you revert back to a hazard-based warning system? So I think these are really interesting questions that we can start to look into a little bit more as we go forward. I'll leave it there. Went through really quickly, but thank you very much. I'm happy to take questions or connect with me on LinkedIn.
I'm muted. Yeah. Thank you so much, Sally, for this amazing presentation. And with this, we are wrapping up our session for today. Thank you to all the speakers and the participants for being with us. We hope to see you tomorrow for our third session, where we will be learning and discussing about how surveys provide applicable insights to national meteorological and hydrological services. And we also have 2 more sessions on Thursday. Hope to see you there as well. Thank you so much.